Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists not in the physical realm of our universe, but in the gentle landscape of imagination and wonder. I want to take you to a place where the very fabric of reality moves differently, where the fundamental rules that govern our existence have been quietly rewritten, and where the speed of light itself has slowed to a gentle crawl of just 1 mile per hour. Before we begin this journey together, I'd love to know where you're joining me from tonight. What corner of our beautiful planet are you resting in right now? What time is it where you are? Are you tucked into bed, perhaps with the lights dimmed low? Or maybe you're settling into a comfortable chair, ready to let your mind wander through the cosmos. If this journey resonates with you, if these gentle explorations of cosmic possibility bring you peace, I invite you to like this video and subscribe to join our community of dreamers and wanderers. But do so only if it feels right, only if this moment of connection feels like something you'd want to return to. There's no urgency here, no pressure, just an open invitation to explore together whenever you need a moment of cosmic calm. It's a question that might sound impossible at first, perhaps even absurd when you first encounter it. The speed of light, after all, is one of the fundamental constants of our universe, racing through the vacuum of space at approximately 182 miles per second, a velocity so tremendous that it can circle our entire planet more than 7 times in a single heartbeat. And yet, what if we could imagine, just for tonight, just for these quiet hours we're sharing together, that light moved not at this incomprehensible speed, but at the pace of a gentle evening walk? What if every photon, every particle of light that carries information and energy through our universe, drifted through space at just 1 mile per hour, no faster than you might stroll through a peaceful garden on a summer evening? This isn't a scientific proposal, of course. We're not suggesting that the universe actually works this way, or that physics could somehow be rewritten. Instead, we're embarking on a thought experiment, a gentle exploration of what reality might feel like if one of its most fundamental properties were dramatically different. Think of it as a form of cosmic meditation, a way of understanding our actual universe by imagining it transformed, slowed down to a pace where we can truly observe and appreciate every detail of how light shapes our existence. In our everyday lives, light seems instantaneous. You flip a switch and the room illuminates immediately. You look at the moon and you see it as it appears right now, or at least close enough that the difference doesn't matter to your perception. But even in our real universe, light takes time to travel. The sunlight warming your face left the surface of our star about 8 minutes and 20 seconds ago. The light from the nearest star system, Alpha Centauri, has been travelling for over 4 years before it reaches your eyes. And the light from distant galaxies has been journeying for millions or even billions of years, carrying with it images of a universe that no longer exists in quite the same form. Now, imagine if we could slow this cosmic messenger down even further. Imagine if light, instead of racing across the 93 million miles between Earth and the Sun in just over 8 minutes, took over 10,000 years to make that same journey. Imagine if the light from your bedside lamp took several seconds to reach your eyes, or if the glow from your phone screen arrived at your retinas with a noticeable delay. This is the universe we're going to explore together tonight, a cosmos where every interaction with light becomes a patient meditative experience, where the act of seeing itself becomes a form of waiting, and where the present moment stretches out into something far more complex and layered than we typically experience. In this slow light universe, the very nature of perception would be transformed. When you look at anything, you wouldn't see it as it is now, but as it was moments, minutes, hours, or even days ago, depending on the distance. Your reflection in a mirror wouldn't be instantaneous, but would show you a version of yourself from seconds past. A conversation with someone across a room would involve not just the delay of sound, which travels at about 767 miles per hour through air at sea level, but also a visual delay as the light carrying their image crawls toward you at its leisurely 1 mile per hour pace. Every visual interaction would become a kind of time travel, a glimpse into the recent past rather than the immediate present. Consider for a moment how this would change the simple act of watching a sunset. In our world, when the sun dips below the horizon, the transition from day to night happens relatively quickly. The sky transforms through its palette of colours in a matter of minutes, and darkness settles over the landscape within an hour or two, depending on your latitude and the time of year. But in our slow light universe, this daily transformation would become an epic event lasting days or even weeks. The last rays of sunlight would continue to arrive long after the sun itself had set, painting the sky in a prolonged symphony of colours that would gradually fade as the final photons completed their unhurried journey from the horizon to your eyes. The implications extend far beyond just visual perception. In our universe, electromagnetic radiation, which includes not just visible light but also radio waves, microwaves, infrared radiation, ultraviolet light, X-rays and gamma rays, all travel at the same fundamental speed, the speed of light. If we slow down light to 1 mile per hour, we're also slowing down all of these other forms of electromagnetic radiation. Radio communications would take hours or days to travel the distances they currently cover in fractions of a second. Television broadcasts would become exercises in extreme patience. The GPS satellites that help navigate our world would be essentially useless, their signals taking so long to reach Earth that any position information would be hopelessly outdated by the time it arrived. But perhaps there's something beautiful in this imagined slowness, something that speaks to a deeper part of our consciousness that yearns for a less hurried existence. In our actual universe, we often feel overwhelmed by the speed of information, by the instantaneous nature of modern communication, by the constant bombardment of stimuli travelling to us at light speed. What if, instead, every piece of information had to make a slow, deliberate journey to reach us? What if we had time to prepare for each arriving image, each incoming message, each new piece of knowledge about the world around us? As we settle deeper into this thought experiment, let's consider what it would mean for our understanding of space itself. In physics, space and time are intimately connected, woven together into the fabric of space-time. The speed of light serves as the fundamental link between these two aspects of reality, determining how quickly causes can create effects across distances. When we imagine slowing light down to 1 mile per hour, we're not just changing how quickly things appear to happen, we're fundamentally altering the relationship between space and time, between here and there, between now and then. In our slow light universe, the concept of simultaneity would become even more complex and relative than it already is in our actual universe. According to Einstein's theory of special relativity, there is no absolute simultaneity. Whether two events happen at the same time depends on the observer's frame of reference. This effect is usually only noticeable at very high speeds or across vast cosmic distances, but in a universe where light crawls along at 1 mile per hour, these relativistic effects would become part of everyday experience. Two people standing at opposite ends of a football field would disagree about when events in the middle of the field occurred, not by microseconds, but by noticeable fractions of a second or even full seconds. The night sky in this universe would tell an even more dramatic story of time's passage. When you look up at the stars in our real universe, you're already looking back in time. The light from Polaris, the North Star, left that star about 433 years ago. The light from the Andromeda Galaxy has been travelling for about 2.5 million years. But if light moved at only 1 mile per hour, these cosmic distances would translate into truly incomprehensible time delays. The light from the Moon, our nearest celestial neighbour at about 238,900 miles away, would take over 27 years to reach Earth. The light from the Sun would take over 10,000 years, and the light from even the nearest stars would take so long to arrive that it would exceed the entire history of human civilization many times over. This means that in our slow light universe, astronomy would be impossible in any form we recognise. We could never see the stars at all, at least not with our human lifespans. The night sky would be truly dark, punctuated only by the faint glow of the moon from decades past, and perhaps the planets of our own solar system from years or centuries ago. The grand structure of the universe, the galaxies and nebulae and cosmic web that we've discovered through our telescopes, would be forever hidden from us, their light still crawling through the vast distances of space, not due to arrive for millions or billions of years. Yet perhaps this limitation would inspire a different kind of cosmic awareness. Unable to see the distant universe directly, inhabitants of this slow-light cosmos might develop other ways of understanding their place in the greater whole. They might become masters of inference and deduction, building sophisticated models of what lies beyond their observable horizon. They might develop a deeper appreciation for their immediate surroundings, for the local wonders that their slow light could actually reveal within a human lifetime. Or they might cultivate a profound patience, planning observations and experiments that would take generations to complete, turning science into a multi-generational endeavour where great-great-grandchildren would finally receive the data their ancestors had been waiting for. The very nature of matter and energy would need to be reconsidered in this universe. In our reality, the speed of light appears in many fundamental equations of physics. Einstein's famous E/mc2 tells us that energy and mass are related through the speed of light squared. If c, the speed of light, were only 1 mile per hour instead of 186,282 miles per second, this relationship would be dramatically different. The amount of energy contained in even a tiny amount of matter would be vastly reduced. Nuclear reactions, which power the stars and make life as we know it possible, might not work at all, or might work in completely different ways. But we're not here tonight to rigorously work through all the physics equations and determine exactly how a slow light universe would function at the quantum level. Instead, we're here to dream, to wonder, to let our minds wander through possibilities that stretch our imagination and help us appreciate the remarkable nature of our actual universe. We're here to find peace in contemplation, to let the gentle rhythm of these ideas carry us toward rest and reflection. Think about how photography would work in this slow light world. In our universe, a camera can capture an instant, freezing a moment in time. The exposure might last only 1,000th of a second, capturing light that left the subject at essentially the same moment. But if light travelled at only 1 mile per hour, taking a photograph would be an entirely different process. The camera would need to wait for light from different parts of the scene to arrive. Light from objects just a few feet away might take seconds to reach the lens, while light from a distant mountain might take hours or days. A single photograph would become a temporal collage, combining moments from different times depending on the distance of each element in the frame. Perhaps photographers in this universe would become artists of time rather than artists of light, carefully orchestrating scenes that would unfold over hours or days as the light from different distances slowly accumulated on their sensors. They might create images that could never exist in a single moment, layering time in ways that we can barely imagine. A portrait might capture a person's movement over several minutes, with their face sharp and clear from one distance, while their hands, held at a different distance from the camera, show the blur of all their gestures during the exposure time. The biological implications of slow light would be profound as well. In our world, many organisms depend on the near instantaneous arrival of light for survival. Predators spot prey and strike in fractions of a second. Prey animals detect threats and flee based on visual cues that arrive almost immediately. Plants track the sun across the sky and adjust their leaves and flowers accordingly. In a slow light universe, all of these interactions would need to work differently. Evolution would have taken entirely different paths, perhaps favouring organisms that could predict where things would be, rather than simply responding to where they appear to be. Imagine a forest in this slow, light world. The canopy above would be a shifting mosaic of light and shadow, with sunbeams taking minutes or hours to filter down through the leaves. Each tree would exist in its own temporal bubble, receiving light from the sun at different times depending on its height and position. The forest floor might still be receiving morning light well into what we would consider afternoon, while the treetops were already bathed in the glow of sunset. It would be a place of perpetual transition, where different layers of time overlap and intermingle in a slow, graceful dance. Human civilization in such a universe would have developed along entirely different lines. Without the ability to see distant objects in real time, navigation would be challenging. Ships at sea couldn't rely on lighthouses that they could see from miles away, as the light would take hours to reach them, showing only where the lighthouse was hours ago, not where it is now. Cities at night would glow with a peculiar kind of beauty, their light spreading outward in slow-motion ripples, each street lamp creating an expanding sphere of illumination that would take minutes to fill the surrounding area. Communication technology would be fundamentally different as well. In our world, we're accustomed to nearly instantaneous communication across vast distances. We video chat with people on the other side of the planet with only a fraction of a second of delay. But if electromagnetic waves travelled at only 1 mile per hour, a phone call to someone in the next town might take hours for the signal to arrive. Global communication as we know it would be impossible. Perhaps people would have developed different technologies, ones that don't rely on electromagnetic radiation, Or perhaps they would have simply accepted that long-distance communication requires patience and planning. The economic implications would be staggering. Our modern economy depends on rapid information transfer. Stock markets, banking systems, and supply chains all rely on the ability to transmit data at light speed. In a slow light universe, these systems would need to be completely reimagined. Perhaps local economies would be far more important, with each community being largely self-sufficient because coordinating with distant places would be so slow and difficult. Or perhaps elaborate predictive systems would have evolved, with people making decisions based on complex models of what they expect to happen, rather than on current information. Weather prediction would be both easier and harder in this strange universe. Easier because weather systems would still move at their normal speeds, while the light informing us about them would be delayed, giving us a kind of temporal buffer. If you could see a storm approaching, you would know it had actually been approaching for hours or days depending on the distance. But harder because gathering real-time data about current conditions would be nearly impossible. Meteorologists would need to work with information that was hours or days old, trying to extrapolate from past states to predict future ones without ever really knowing the present state. Art and culture in a slow light universe would reflect these different relationships with time and perception. Perhaps patience would be the highest virtue, celebrated in stories and songs. Maybe their mythology would be filled with tales of messages that took lifetimes to arrive, of lovers separated not just by distance, but by the fundamental delay of light itself. Their architecture might be designed around the slow propagation of light, with buildings that reveal themselves gradually as illumination creeps across their surfaces, telling stories in the unfolding of shadows and highlights over hours or days. Music might take on a different character entirely. In our world, we can have large orchestras play together because the speed of light allows conductors to be seen essentially instantaneously by all musicians. But if light crawled along at 1 mile per hour, a conductor standing even 20 feet from the back row would be seen with a noticeable delay. Musicians would need to anticipate the conductor's movements, or perhaps music would be more decentralized, with each section operating more independently, creating layered compositions where synchronization is impossible, but harmony emerges from the acceptance of delay. As we continue to explore this imagined universe, we begin to see how profoundly light shapes every aspect of our existence. It's not just about vision or communication, it's about the fundamental way that cause and effect propagate through space. In our universe, when you push a button, the electrical signal travels to its destination at a significant fraction of the speed of light. The response seems instantaneous. But in our slow light universe, pushing a button might not produce a result for seconds, minutes, or even hours, depending on how far the signal needs to travel. This would change the very psychology of action and reaction. In our world, we're accustomed to immediate feedback. We click a mouse and see the result on our screen instantly. We flip a switch and the light comes on right away. This immediate feedback shapes how we think and learn, how we understand cause and effect. In a slow light universe, every action would require faith that the intended effect would eventually occur, even if you couldn't see it immediately. Patience wouldn't just be a virtue, it would be a necessity for navigating daily life. Consider what childhood development would be like in such a universe. Babies learn about the world through interaction, through seeing the immediate results of their actions. They learn that crying brings comfort, that reaching for objects allows them to grasp them, that smiling at faces brings smiles in return. But if light moved at only 1 mile per hour, these fundamental learning experiences would be different. A baby might cry and not see their parents' concerned face for several seconds. They might reach for a toy and have to wait for the visual confirmation that their hand has grasped it. The development of hand-eye coordination, so crucial to human development, would need to work in entirely different ways. Perhaps humans in this universe would develop other senses more strongly. If sight were so delayed as to be impractical for immediate interactions, maybe hearing or touch would become dominant. Or perhaps they would develop a kind of predictive sight, learning from birth to unconsciously calculate where things actually are based on where they appear to be and how far away they seem. Their brains might be wired differently, with regions dedicated to temporal calculation and prediction that we don't possess. Sports and games would be fascinating in this slow light world. Imagine trying to play tennis when you see the ball where it was several seconds ago, not where it is now. Players would need to develop an entirely different kind of skill, predicting trajectories not based on what they see, but on mental models and perhaps other sensory input. Or perhaps sports would be more contemplative, focused on strategy and position rather than quick reflexes. Chess might still work well, but it would be played with the understanding that you see your opponent's move several seconds after they make it, adding another layer of complexity to the game. The concept of privacy would be different too. In our world, we can close curtains and immediately block the view from outside. But if light moved at 1 mile per hour, closing curtains would only prevent new light from escaping. Light that had already left would continue its slow journey outward, carrying images of whatever was happening before the curtains were closed. Privacy would require planning ahead, anticipating when you would want visual barriers in place. As we near the end of this first chapter of our journey, let's take a moment to appreciate the profound strangeness and beauty of this imagined universe. It's a cosmos where time and space are even more intimately connected than in our own, where every glance is a look into the past, where patience is not just a virtue but a fundamental requirement for existence. It's a universe that challenges our most basic assumptions about how reality works, forcing us to reconsider things we take for granted every moment of our lives. And yet, in some ways, this slow-light universe might offer its own forms of grace and beauty. Without the constant bombardment of instant information, perhaps its inhabitants would live more contemplative lives. Without the ability to see immediate results, perhaps they would be better at long-term thinking and planning. Without the distraction of distant stars, perhaps they would find deeper meaning in their immediate surroundings, in the slow dance of light through their local environment. As you lie there tonight, perhaps beginning to feel the gentle pull of sleep, consider how the speed of light shapes your own experience. Notice how you see the world around you, as if it were all happening now, even though you're actually seeing a collection of moments from the very recent past. The wall across your room is a few nanoseconds ago. The moon, if you can see it through your window, is about 1.3 seconds ago. The stars are years, centuries, or millennia ago, their light having travelled across vast cosmic distances to reach your eyes just now. We live in a universe where light is fast enough to give us the illusion of instantaneous sight, but slow enough that the cosmos has a history written in light itself. We can look out into space and see the universe as it was billions of years ago, watching galaxies as they were when the universe was young. This is a gift of the actual speed of light, neither too fast nor too slow, but precisely what it needs to be for the universe to work the way it does, for stars to shine, for planets to form, for life to evolve, and for conscious beings like us to contemplate it all. We ease into the scale of the cosmos now, you and I, as we continue, our gentle exploration of a universe where light drifts along at just 1 mile per hour. In this second phase of our journey, we're going to stretch our perception outward, from the intimate spaces of rooms and buildings to the vast expanses of continents, planets, and the solar system itself. We're going to discover how, in this imagined cosmos, every measurement of distance becomes fundamentally a measurement of time, and how the simple question, how far, transforms into the more profound question, how long? Let's begin with something familiar, something close and comforting. Picture yourself in your room right now, wherever you are in the world as you listen to these words. In our real universe, light from your bedside lamp reaches your eyes in about 10 nanoseconds if you're 3 feet away. It's so fast that your brain cannot possibly perceive any delay. But in our slow light universe, that same 3 feet would require light to travel for about 2 seconds. When you turn on your lamp, you would watch as a sphere of illumination slowly expands from the bulb, crawling across the nightstand, creeping up the wall, gradually revealing the room around you like a slowly blooming flower of light. Now imagine walking across this room. As you move, you're not just travelling through space, you're travelling through different moments of time. The far wall that you're approaching shows you what was happening there several seconds ago. The floor beneath your feet is lit by light that left the ceiling lights moments in the past. Every step you take carries you through a landscape of overlapping temporal zones, each object existing in its own slice of the recent past, the delay determined entirely by its distance from your eyes. This transformation of distance into time would fundamentally alter how we understand and navigate our immediate environment. A hallway stretching 50 feet would represent about half a minute of light travel time. Walking down it would be like moving through a tunnel of time, where the far end shows you what was there 30 seconds ago, while the walls beside you are only a second or two in the past. If someone was standing at the far end of the hallway and began walking toward you, you wouldn't see them start moving for half a minute. By the time the light carrying the image of their first step reached your eyes, they would have already covered significant distance, perhaps even reached you, creating a bizarre situation where someone could arrive before you see them begin their journey. Let's expand our view now to encompass a house or apartment building. In our real universe, you can look out your window and see your neighbour's window across the courtyard instantly, perhaps wave to them and see them wave back with no perceptible delay. But if light travelled at only 1 mile per hour and your neighbour's window was just 100 feet away, it would take over a minute for their image to reach you. You might wave good morning to them, then go make coffee and return to see them finally waving back, though they had actually returned your wave immediately. Every visual interaction across even modest distances would become a slow exchange of temporal messages. The architecture of buildings themselves would likely evolve differently in such a universe. Without the ability to see the whole structure at once in real time, architects might design buildings that tell stories through the propagation of light, structures that reveal themselves gradually as illumination spreads. Imagine towers with lights that turn on in sequence, creating patterns that would take hours to fully develop as the light from each level slowly reaches observers at different distances. Buildings might be designed not just as spatial structures, but as temporal experiences, unfolding over time for anyone watching from afar. Now, let's step outside and consider a city block. In our world, you can stand at one corner and see the entire block essentially instantaneously. You see pedestrians, cars, shops, and trees all in what feels like the same moment. But in our slow light universe, a city block stretching 300 feet would represent about 3.5 minutes of light travel time. Standing at one corner, you would see the far corner as it was 3.5 minutes ago. A bus travelling down the street would appear in multiple positions simultaneously, its current position invisible to you, its past position still visible as the light from its journey continues to arrive. This would make city life extraordinarily complex. Traffic lights would need to account not just for the actual positions of vehicles, but for where they appear to be to different observers. Pedestrians crossing streets would need to predict where cars actually are, not where they see them. Perhaps cities would develop elaborate systems of sound signals, since sound, travelling at 767 miles per hour, would actually be much faster than light in this universe. The honk of a horn would arrive long before the image of the car that produced it. Let's continue expanding our view to encompass an entire city. A city with a diameter of 10 miles would span 10 hours of light travel time. Standing on a hill overlooking the city, you wouldn't see the city as it is now, but as a temporal gradient, with the nearest neighbourhoods showing their state from minutes ago, while the far side of the city displays what was happening 10 hours in the past. You might see the sunrise on one side of the city while the other side still appears to be in darkness, not because the sun hasn't risen there yet, but because the light showing you that sunrise hasn't had time to cross the city to reach your eyes. Imagine what a day in such a city would be like. You wake up in the morning and look out your window. The building across the street appears to still be in darkness, its windows dark, though you know the sun has been up for a while. Slowly, over minutes, you watch as the light from sunrise creeps across the facade, windows beginning to glow one by one as the expanding sphere of sunlight finally reaches them from your perspective. You leave for work, and as you travel across the city, you move through different temporal zones. The downtown area that you're heading toward appears as it was hours ago when you first glimpse it in the distance. As you approach, you watch it fast forward through its morning, catching up to something closer to the present the nearer you get. Your workplace, when you finally arrive, exists in multiple states simultaneously from your perspective. The lobby that you've just walked through shows its state from seconds ago. Your office on the 10th floor, glimpsed through a window, shows what was happening there 5 or 6 minutes ago. Your colleagues appear to be in multiple places at once, their past selves still visible in locations they've already left, their current positions not yet visible to you. Meetings would be particularly challenging. In a conference room, people sitting around a table would each see the others with different delays based on distance. Someone across the table, perhaps 10 feet away, would appear as they were 7 or 8 seconds ago. Their words would arrive much faster than their image, creating a disconnect between what you hear and what you see. Perhaps people would learn to close their eyes during conversations, relying on sound rather than sight, or perhaps they would develop new social protocols that account for these delays. Now let's expand our view even further to encompass entire countries and continents. The United States, stretching roughly 2,800 miles from coast to coast, would span 2,800 hours of light travel time, about 117 days. Standing on the Atlantic coast and looking west, if such a thing were possible with the Earth's curvature, you would see the Pacific coast as it was almost 4 months ago. You would be looking at a different season, seeing California's summer while experiencing autumn in New York, not because the seasons are actually different, but because the light from California's present hasn't reached you yet. This would make weather monitoring and prediction incredibly complex yet strangely advantageous in some ways. A storm system moving across the country at, say, 30 miles per hour would actually be moving faster than light in this universe. The storm would arrive before its image does. You might experience rain and wind while the sky still appears clear, the image of the storm cloud still crawling toward you at light sluggish pace. Meteorologists would need to rely on networks of sound-based or physical sensors rather than satellite imagery, which would be hopelessly delayed. Communication across continents would require extraordinary patience. A video call from New York to London, about 3,500 miles apart, would involve a delay of 3,500 hours, about 146 days, for the image to travel one way. You could speak to someone in London and not see their reaction for nearly 5 months. By the time you saw them respond, seasons would have changed, entire life events could have occurred. Perhaps people would communicate through written messages or audio recordings, accepting that visual communication across such distances is impractical within human timescales. The implications for governance and civilization would be profound. How could a nation function when different parts of it are separated not just by distance, but by months of communication delay? Perhaps societies would organize themselves into small local communities, each largely autonomous because coordination over large distances would be so difficult. Or perhaps they would develop predictive governance systems, with leaders making decisions based on models and projections rather than current information. Let's venture even further now and consider our entire planet. Earth, with a circumference of about 20^901 miles at the equator, would be wrapped in layers of time. Light from the opposite side of the planet would take over 1,000 days to reach you, nearly 3 years. The International Space Station, orbiting at an altitude of about 250 miles, would be visible only as it was 250 hours ago, over 10 days in the past. Satellites in geostationary orbit, about 22,236 miles above the equator, would appear as they were over 2.5 years ago. This would make global awareness impossible in any conventional sense. You could never know what was happening on the other side of the world in anything approaching real time. News would be ancient history by the time it arrived. A volcanic eruption in Japan wouldn't be visible from America for years. The Olympics would be over for years before people on the other side of the world could watch them. Perhaps each region of the world would develop in isolation, unaware of what was happening elsewhere except through written records carried by travelers, like a return to the age of sailing ships but for fundamentally different reasons. The Moon, our constant companion in the night sky, orbits at an average distance of about 238,900 miles from Earth. In our slow light universe, moonlight would take 230,900 hours to reach us, about 27 years. The moon you see in the sky wouldn't be where the moon is now, but where it was nearly 3 decades ago. A full moon would be showing you the lunar surface as it was illuminated when you were decades younger, or perhaps before you were even born. The phases of the moon would be completely disconnected from the actual position of the moon, sun, and Earth. You might see a full moon in the sky while knowing that the moon itself is currently new, its dark side facing Earth, but that image won't arrive for another 27 years. This temporal displacement would make lunar observation and exploration incredibly challenging. If humans in this universe somehow managed to send a mission to the moon, mission control would be seeing the spacecraft as it was 27 years ago. The astronauts would have to operate entirely autonomously, as any guidance from Earth would be decades out of date. Perhaps they would leave detailed records for future generations to study, knowing that their triumph or tragedy wouldn't be visible from Earth until long after it occurred. Now let's venture out into our solar system, where the distances become truly staggering even by slow light standards. The Sun, at about 93 million miles from Earth, would be separated from us by 93 million hours of light travel time, about 10,616 years. The sunlight warming your face wouldn't have left the sun in recent history, or even in recorded human history. It would have begun its journey when humans were just developing agriculture, when the last ice age was ending, when mammoths still walked the earth. This means that in our slow light universe, the sun that appears in the sky is not the sun as it exists now, but the sun as it was over 10,000 years ago. If the sun were to suddenly change, if it were to grow dimmer or brighter, if it were to undergo some dramatic transformation, we wouldn't know for millennia. We would continue to receive ancient sunlight, oblivious to whatever might be happening to our star in the present moment. The very concept of solar observation would be meaningless. By the time we saw anything happen on the sun, civilizations would have risen and fallen, languages would have evolved beyond recognition, the entire course of human history would have played out. The planets of our solar system would be even more temporally displaced. Mars, when it's closest to Earth at about 34 million miles, would appear as it was about 3,900 years ago. When it's farthest from us at about 250 million miles, we would see it as it was over 28,000 years in the past. Jupiter, ranging from 365 million to 601 million miles from Earth, would show us images from 41,000 to 68,000 years ago. Saturn would be visible as it was 91,000 to 114,000 years ago. Uranus and Neptune would be so temporally distant that we would be seeing them as they were hundreds of thousands of years in the past. This would make planetary astronomy an exercise in deep time observation. Each planet would appear to us not as a contemporary neighbour in our solar system, but as an ancient relic, its image preserved in the slowly crawling light that carries its appearance across the vast distances of space. The movements of the planets, their orbits around the Sun, would be impossible to track in any meaningful way. By the time we saw a planet complete one orbit, numerous generations would have passed, and the accumulated observations would be more like archaeological records than scientific data. Consider what this means for our understanding of the solar system as a dynamic, interconnected system. In our real universe, we can observe the planets, track their movements, predict their positions, and understand the gravitational dance they perform around our star. We can send spacecraft to visit them and receive data back within hours. But in our slow light universe, each planet would be an island in time, separated from us not just by space but by millennia or tens of millennia of light travel delay. The asteroid belt scattered between Mars and Jupiter would be a temporal mosaic, with each asteroid visible as it was at a different point in the deep past. Comets approaching the inner solar system would be invisible until long after they had passed. Meteor showers would be seen decades or centuries after the Earth had actually passed through the debris field. The entire solar system would exist in a state of temporal fragmentation, with no two objects visible in their contemporary states. Yet perhaps there would be a strange beauty in this temporal isolation. Each celestial body would be like a message from the deep past, a glimpse into history preserved in light. The night sky, though mostly dark due to the absence of visible stars, would contain these few visible planets, each one a time capsule from a different epoch. Observers would know that they're seeing Mars as it was during the Bronze Age, Jupiter as it was when Neanderthals walked the Earth, Saturn as it was during the last ice age. Space exploration in such a universe would be essentially impossible with any technology we can imagine. Even if spacecraft could be built and launched, they would disappear into the darkness the moment they left Earth, their image taking years or decades to catch up with their actual position. Ground control would have no way to track them, guide them, or even know if they had survived their journey. Perhaps space exploration would be more like sending messages in bottles into an ocean, hoping that someday, somehow, evidence of their journey might return. The concept of space weather would be meaningless in any practical sense. Solar flares, coronal mass ejections, and other solar phenomena that can affect Earth would have occurred 10,000 years before their effects reached us. By the time we saw a solar storm beginning on the Sun's surface, it would be ancient history, its particles having long since either struck Earth or passed by harmlessly. We could never prepare for or predict space weather events because we would have no current information about the Sun's activity. This brings us to an interesting paradox in our slow light universe. While electromagnetic radiation, light, radio waves, etc., would travel at only 1 mile per hour, the actual particles ejected from the Sun during solar storms would travel at their normal speeds, typically around 300 to 500 miles per second for the bulk of the material. This means that the physical effects of a solar storm would arrive at Earth thousands of years before we could see the storm happening on the Sun. We would experience the aurora, the magnetic disruptions, the radiation, all while the Sun appeared calm and peaceful in our sky, its turbulent activity still hidden in light that wouldn't arrive for millennia. As we contemplate these vast scales of time and distance, we begin to see how fundamentally the speed of light shapes our relationship with the cosmos. In our real universe, light is fast enough that we can have a coherent, if delayed, view of our solar system. We can see the Sun as it was 8 minutes ago, the planets as they were minutes or hours ago, and maintain a reasonably current understanding of our cosmic neighbourhood. But slow light down to a walking pace, and that coherent view dissolves into a fragmented collection of images from vastly different times. The psychological impact of living in such a universe would be profound. Humans would grow up knowing that they can never see the present beyond their immediate surroundings. They would understand from childhood that everything they see in the distance is old, that the farther away something is, the more ancient its image. Perhaps they would develop a different relationship with time itself, seeing it not as a flowing river but as a series of nested shells, each distance representing a different layer of the past. Education would need to account for this temporal complexity. Children would learn that when they see the Sun in the sky, they're looking at ancient history. They would study the positions of planets not through observation but through calculation and prediction, using mathematical models to understand where things actually are rather than where they appear to be. Geography lessons would include temporal components. This city is 500 miles and therefore 500 hours in the past. That mountain range is 50 miles and 50 hours ago. Perhaps art and literature in this universe would reflect this temporal fragmentation. Stories might be told from multiple temporal perspectives, acknowledging that different characters in different locations are seeing different versions of the past. Paintings might attempt to capture not a single moment but the layered moments visible from a single viewpoint, with near objects painted as they appear now and distant objects as they appeared hours, days, or years ago. The concept of photography, which we touched on in the first chapter, would be even more complex when dealing with landscapes and distant subjects. A photograph of a mountain range might capture the near foothills as they were hours ago, the middle peaks as they were days ago, and the distant summits as they were weeks or months in the past. Seasonal changes would be visible in a single image. Spring flowers in the foreground, winter snow on the distant peaks, not because the seasons are actually different, but because the light from different distances carries images from different times of year. Movies and video would be almost impossible to create in any form we would recognize. The delay between action and visibility would mean that filming a scene would require extraordinary coordination and patience. An actor might perform their part, but their image wouldn't reach the camera for seconds or minutes depending on distance. Editing would be a nightmare of temporal synchronization. Perhaps visual storytelling would be abandoned in favor of audio dramas, or perhaps entirely new forms of time-based art would evolve. Music and sound would take on increased importance in this universe. While sound is much slower than light in our world, travelling at about 767 miles per hour through air at sea level, in our slow light universe, sound would be 767 times faster than light. You would hear thunder hours before seeing lightning. You would hear someone calling from across a field long before seeing them wave. Perhaps cultures would develop rich acoustic traditions, with architecture designed for sound rather than sight, and communication based primarily on audio rather than visual signals. The biological implications continue to fascinate as we consider larger scales. Migrating birds that navigate by the sun would need to account for the fact that the sun they see is not where the sun actually is. Perhaps they would evolve different navigation methods, using magnetic fields or other cues that don't depend on light. Plants that track the sun across the sky would be following an ancient path, their leaves and flowers turning to face where the sun was hours ago, not where it is now. Ecosystems would be shaped by these temporal delays. A forest fire's smoke would be smelled and felt long before it was seen. Predators and prey would interact based on sound, smell, and vibration rather than sight. The visual beauty of nature, the colours of flowers, the patterns of butterfly wings, the displays of peacocks, might never have evolved, or might serve completely different purposes than attracting mates or warning predators. As we near the end of this second chapter, let's take a moment to appreciate the profound transformation we've imagined. By slowing light to a walking pace, we've turned distance into time in the most literal sense. Every mile becomes an hour of delay, every foot becomes seconds of temporal displacement. The universe becomes not a collection of objects in space, but a collection of moments scattered across time, each one frozen in the slowly propagating light that carries its image outward. This thought experiment helps us understand something crucial about our actual universe. The finite speed of light, even at its tremendous actual velocity, means that we always see the universe as it was, never as it is. We are fundamentally separated from the present moment of distant objects, imprisoned in our light cone, able only to observe the past. But in our real universe, light is fast enough that for most human purposes, this delay doesn't matter. We can function as if we see things instantaneously, even though we never actually do. In our slow light universe, this comforting illusion would be shattered. The delay would be impossible to ignore, forcing its inhabitants to confront the temporal nature of perception constantly. Every glance would be a reminder that the present is unreachable, that we are always and forever observers of the past, that the universe we see is a construction of moments that have already occurred, preserved in the light that slowly carries them to our eyes. In the quiet of night, in this imagined universe where light creeps along at just 1 mile per hour, you look up at what should be a sky full of stars, and instead you find something profoundly different. A vast darkness punctuated perhaps by only the faintest suggestions of light, each photon a messenger from the deep past, still journeying toward Earth after millennia of travel. Tonight, in this third chapter of our exploration, we're going to discover what happens to the heavens themselves when light moves so slowly that starlight becomes not a nightly gift but a geological inheritance, passed down through countless generations who never see its arrival. Let's begin with the most fundamental change, the absence of visible stars. In our real universe, the nearest star to Earth beyond our Sun is Proxima Centauri, part of the Alpha Centauri system, at a distance of about 4.24 light-years, or roughly 25 trillion miles. When light travels at 186,282 miles per second, that journey takes just over 4 years. But if light travelled at only 1 mile per hour, that same journey would take 25 trillion hours, or about 2.85 billion years. The light from Proxima Centauri that departed when the star was young would still be crawling through the vast emptiness of interstellar space, not due to arrive at Earth for billions of years to come. This means that in our slow light universe, the night sky would be truly dark in a way that we can barely imagine. No stars would be visible to the naked eye, no constellations would pattern the darkness, no Milky Way would arch across the heavens. The only celestial objects visible would be those within our own solar system, and even these would be dramatically transformed by the temporal delays we explored in the previous chapter. The night sky that has inspired humanity throughout history, that has guided navigation and sparked mythology, that has made us wonder about our place in the cosmos. This sky would simply not exist. Consider what this means for the development of human consciousness and culture. In our world, the stars have been constant companions to humanity, inspiring our earliest religions, our poetry, our science. We've used them to navigate across oceans, to mark the seasons, to tell stories that connect us to something larger than ourselves. But in a universe where starlight takes billions of years to arrive, humans would evolve and develop civilization under empty skies. They would have no concept of stars as distant suns, no understanding that the universe extends beyond their solar system, no visual evidence that they are part of a vast cosmic web of galaxies and nebulae. Yet perhaps this absence would inspire its own forms of wonder. Unable to see the stars, inhabitants of this universe might develop rich mythologies about what lies beyond the darkness. They might imagine the night sky as a vast ocean of invisibility, hiding wonders that can never be seen but only imagined. Their religions might speak of light that is always coming but never arrives, of messages sent from the beginning of time that are still travelling toward them. The darkness itself might become sacred, a canvas for projection and imagination, unlimited by actual celestial objects. Let's think about what would be visible in this night sky. The moon, as we discussed, would appear as it was 27 years ago, its light having taken that long to traverse the 238,900 miles between Earth and its satellite. But here's where things become even more interesting. The moon doesn't generate its own light, it reflects sunlight. So the moonlight reaching Earth would actually be sunlight that left the sun over 10,000 years ago, reached the moon 27 years ago, and has been travelling from the moon to Earth ever since. We would be seeing the moon illuminated by truly ancient sunlight, a cascade of temporal delays that stretches back to before human civilization began. The phases of the moon would be completely disconnected from any intuitive understanding of the Sun-Earth-Moon relationship. You might look up and see a full moon, knowing that the moon itself is currently new, or vice versa. The moon would appear to go through its phases, but these phases would be showing you the moon's relationship with the sun, as it was 27 years ago, not as it is now. Predicting what phase the moon would appear to be in would require complex calculations, accounting for all these delays. Lunar eclipses would be even stranger. In our world, a lunar eclipse occurs when Earth passes between the sun and moon, casting Earth's shadow on the lunar surface. We see this happen in real time, watching Earth's shadow creep across the moon over the course of a few hours. But in our slow light universe, you would be seeing an eclipse that actually happened 27 years ago. The moon might currently be in full sunlight, but you would see it darkened by an ancient shadow. Even more bizarrely, the shadow itself would be from Earth as it was 27 years ago, blocking sunlight from over 10,000 years ago. Solar eclipses would be practically impossible to observe in any meaningful way. A solar eclipse occurs when the moon passes between Earth and the sun, blocking the sun's light. But if sunlight takes 10,000 years to reach Earth, and the moon's current position is invisible, with its image from 27 years ago visible instead, how could anyone predict or observe an eclipse? You might experience the darkness of an eclipse, feeling the temperature drop as ancient sunlight is blocked by the moon's current position, but you wouldn't see the moon actually covering the sun's disk for another 27 years. The planets would each occupy their own temporal bubble in the night sky. Venus, when closest to Earth at about 25 million miles, would appear as it was about 2,150 years ago. When farthest from us at about 162 million miles, we would see it as it was over 18,000 years in the past. Its phases, like the moon's, would be temporal echoes, showing us ancient configurations of Sun, Venus, and Earth that no longer exist. Mars would tell an even older story. At its closest approach of about 34 million miles, we would see Mars as it was during the time of ancient Egypt's earliest dynasties. At its farthest, about 250 million miles, we would be looking at Mars as it was when humans were still in the Stone Age, when Neanderthals walked the Earth alongside our ancestors. The famous red colour of Mars would be the colour it had millennia ago, and any changes to its surface, dust storms, polar cap variations, even potential asteroid impacts, would be invisible to us for thousands of years after they occurred. Jupiter, the giant of our solar system, would appear as a point of light from 41,000 to 68,000 years in the past, depending on our relative positions in our orbits. The Jupiter we see would be the Jupiter of the Paleolithic era, when humans were creating the first cave paintings, developing language, spreading across the globe. Its great red spot, that enormous storm that has raged for centuries in our time, might not even exist yet in the image we see, or it might exist but be invisible to us for tens of thousands of years to come. Saturn, with its magnificent rings, would be visible as it was 91,000 to 114,000 years ago. We would be seeing Saturn as it was during the last ice age, when massive glaciers covered much of the northern hemisphere, when sea levels were hundreds of feet lower than today. The rings themselves, which may be relatively young in cosmic terms, might appear different in structure or brightness from their current state, but we would have no way of knowing what they look like now. The outer planets, Uranus and Neptune, would be so temporally distant as to be almost mythological. Uranus, at distances ranging from 1.6 to 1.98 billion miles from Earth, would appear as it was 182,000 to 226,000 years ago. Neptune, even more distant at 2.7 to 2.9 billion miles, would show us its state from 308,000 to 331,000 years in the past. These would be glimpses into geological time, into eras before modern humans evolved, when different species of hominids walked the Earth. But here's a thought that adds another layer of complexity to our slow light night sky: orbital motion. All of these planets are moving in their orbits around the Sun, and Earth is moving in its orbit as well. In our real universe, we can track these motions night by night, watching planets move against the background of stars. But in our slow light universe, the apparent position of each planet would be where it was years, centuries, or millennia ago. The actual planet would be somewhere else entirely, invisible in the darkness, its current position only calculable through mathematical models. This would make the motion of planets across the sky extraordinarily complex. You would see Mars appearing to move, but this motion would be Mars's movement from thousands of years ago. Meanwhile, the actual Mars would be elsewhere, and the light from its current position wouldn't arrive for thousands of years. The result would be a sky where nothing is where it appears to be, where every celestial object is a ghost of its past self, haunting a position it abandoned long ago. Meteor showers would take on an entirely different character in this universe. In our world, meteor showers occur when Earth passes through the debris trail left by a comet. We see meteors as streaks of light when these particles enter our atmosphere and burn up. The light from this burning reaches our eyes essentially instantaneously. But in our slow light universe, while the meteors would still enter the atmosphere and burn up at their normal speeds, the light from their burning would spread outward at only 1 mile per hour. Imagine a meteor burning up 50 miles above your head. The light from its fiery descent would take 50 hours to reach you. You wouldn't see a quick streak across the sky, but rather nothing at first. Then, hours later, a glowing point would appear in the sky where the meteor had been, slowly fading as the expanding sphere of light from its brief burn finally reaches your eyes. A meteor shower wouldn't be a display of shooting stars, but a gradual appearance of fading points of light, each one marking where a meteor had burned up hours or days before. The aurora borealis and aurora australis, the northern and southern lights, would be transformed beyond recognition. These displays occur when charged particles from the sun interact with Earth's magnetic field and atmosphere, causing atoms to emit light. In our world, we see these emissions essentially as they happen, watching curtains of green, red, and blue light dance across the polar skies. But if light travelled at only 1 mile per hour, the aurora would be invisible at first, even as the particles were actively causing atmospheric atoms to glow. The light from aurora occurring at an altitude of 60 miles would take 60 hours to reach observers on the ground. By the time you saw the aurora, the solar storm that caused it would have long since passed. The dancing curtains of light would be temporal echoes, showing you where energetic particles had been days ago. The entire display would be stretched out in time, with light from different altitudes arriving at different times, creating a strange layered effect unlike anything we see in our real universe. Comets would be particularly mysterious objects in this slow light cosmos. In our universe, we can watch comets approach the inner solar system, develop their characteristic tails as solar radiation heats their icy surfaces, and then retreat back into the outer darkness. But if light moved at only 1 mile per hour, a comet's approach would be invisible until long after it had passed. The light from a comet passing through the inner solar system might take decades or centuries to reach Earth, depending on its trajectory and distance. By the time we saw a comet, it would have long since returned to the outer solar system, or perhaps even completed another orbit. The beautiful tail of a comet, formed by solar wind pushing dust and gas away from the comet's nucleus, would be a fossilized remnant of an ancient passage. We might see comets that no longer exist, having broken apart or been ejected from the solar system, their light still travelling toward us carrying images of their former glory. This raises an interesting question about prediction and observation in our slow light universe. If we can't see celestial objects where they currently are, how could astronomy exist as a science? Perhaps astronomers would be more like historians, studying the deep past rather than the present. They might develop sophisticated mathematical models to predict where things actually are based on where they appear to be, and when that light departed. Astronomy would be an exercise in temporal archaeology, digging through layers of time preserved in slowly arriving light. The zodiacal light, that faint glow visible along the ecliptic caused by sunlight reflecting off dust particles in the solar system, would take on new meaning. Each particle of dust would reflect light from a slightly different time, depending on its distance. The result would be a glow composed of countless different moments, a temporal average of sunlight from various points in the past. It would be like looking at a painting where each brushstroke was made in a different year, but they all somehow combined to create a single image. Let's consider what sunset and sunrise would be like in this universe with our transformed night sky. As the sun sets, its light would continue to arrive for hours after it had dropped below the horizon. The sky wouldn't immediately darken but would fade slowly as the last rays of sunlight complete their mile-per-hour journey from the horizon to your eyes. This twilight would last for hours, a gradual transition from day to night that would make the boundary between them fuzzy and indefinite. As this extended twilight finally fades, the night sky would reveal itself not as a tapestry of stars but as a vast darkness punctuated only by the planets of our solar system, each one a temporal island showing us its state from years, decades, or millennia past. The moon, if visible, would hang in the sky as a reminder of how the heavens looked 27 years ago. The planets would be scattered points of light, each one a messenger from a different epoch of the past. Without stars to define, constellations, how would people navigate at night? In our world, the stars have been crucial for navigation, with Polaris, the North Star, serving as a fixed point that indicates true north. Sailors have used the stars to cross oceans, and travelers have used them to find their way across deserts. But in our slow-light universe, there would be no stellar compass, no celestial map to guide nighttime journeys. Perhaps navigation would rely more heavily on the sun during the day, though even this would be complicated by the temporal delays. The sun you see wouldn't be where the sun actually is, but where it was hours ago depending on its height in the sky. Navigators would need to account for these delays, calculating the sun's actual position based on complex models. Or perhaps magnetic navigation would become dominant, with travelers relying on Earth's magnetic field rather than celestial objects. The absence of visible stars would profoundly impact the development of cosmology and our understanding of the universe's scale. In our world, the discovery that stars are distant suns, that galaxies exist beyond our own, that the universe is vast beyond imagination, all of these revelations came from observing the night sky. But in a universe where starlight takes billions of years to arrive, these discoveries might never be made, or might be made through completely different means. Perhaps scientists in this universe would infer the existence of stars through gravitational effects, noticing subtle perturbations in the orbits of outer planets that suggest massive objects beyond the solar system. Or perhaps they would detect other forms of radiation that somehow travel faster than light in this imagined physics, revealing the presence of cosmic structures invisible to the eye. The history of astronomy would be completely different, possibly more theoretical and mathematical than observational. The cultural impact of this transformed night sky would be immeasurable. Our mythologies are filled with star gods and celestial heroes. Our poetry speaks of wishing on stars, of lovers separated like stars in the sky, of human ambitions reaching for the stars. But in a universe with no visible stars, these metaphors would never develop. The night sky might instead inspire different forms of expression, perhaps poetry about the profound darkness, about the invisible universe that must exist beyond perception, about the patience required to wait for light that may never come. Children growing up in this universe would have a fundamentally different relationship with the cosmos. They wouldn't lie on their backs counting stars or trying to spot satellites passing overhead. They wouldn't learn to identify the Big Dipper or Orion's belt. Instead, they might learn to appreciate the subtle variations in darkness, the slow dance of planets across the sky, the way the moon's phases tell a story of the past rather than the present. The development of telescopes would follow a different path as well. In our world, telescopes revealed progressively more stars, nebulae, and galaxies as they became more powerful. But in our slow-light universe, even the most powerful telescope couldn't reveal stars whose light hadn't arrived yet. Telescopes might instead be used to study the planets in greater detail, to track the slow changes in their appearance over years and decades, to search for patterns in the temporal delays that might reveal something about the nature of light and time. Radio astronomy, which in our world has revealed cosmic structures invisible to optical telescopes, would face the same limitations. Radio waves, travelling at the speed of light, would also move at just 1 mile per hour in our imagined universe. The cosmic microwave background radiation, that faint echo of the Big Bang that fills the universe, would take so long to reach us that it might still be on its way, not due to arrive for billions of years. The universe would be not just optically dark, but silent across the entire electromagnetic spectrum. This brings us to a profound realization about our slow-light universe. It would be a cosmos where the vast majority of existence is hidden from perception, where entire galaxies, nebulae, and cosmic structures exist but cannot be seen, where the universe's history is written in light that is still travelling, still carrying its messages across the impossible distances of space. The inhabitants of this universe would live in a small bubble of visibility, surrounded by an ocean of darkness that hides wonders they can only imagine. Yet perhaps there would be a strange beauty in this limitation, knowing that light from distant stars is on its way, that messages from across the cosmos are slowly approaching, might inspire a different kind of cosmic patience. Civilizations might create time capsules and monuments designed to last billions of years, hoping that someday, when the light from distant stars finally arrives, future beings will be there to witness it. The arrival of starlight would be not a nightly occurrence but a geological event, something that might happen once in the entire history of a planet. Imagine the first time starlight arrives at a planet in this universe. After billions of years of darkness, a point of light appears in the night sky, the first star ever seen. It would be a moment of profound transformation, proof that the universe extends beyond the solar system, that other suns exist in the cosmic darkness. Entire religions might spring up around this event, this first glimpse of the greater cosmos. Scientists would study this single point of light intensely, trying to extract every bit of information from photons that had been travelling since before their planet formed. As more stars slowly became visible over geological time, each one would be a major event. The appearance of a new star in the night sky wouldn't be a discovery but a revelation, a gift from the deep past finally arriving at its destination. The night sky would slowly, over billions of years, begin to fill with points of light, each one marking the end of an epic journey across space and time. But for us, imagining ourselves as inhabitants of this universe at this moment, the night sky remains dark. We stand under a canopy of invisibility, knowing that above us, beyond our perception, exists a universe of unimaginable size and complexity. We know this not because we can see it, but because we've reasoned it out, because we've detected its gravitational influences, because we've imagined what must be there in the darkness. This thought experiment reveals something profound about our actual universe and our relationship with it. We are fortunate that light travels as fast as it does, fast enough to bring us news from across the cosmos within timeframes that, while vast, are at least comprehensible. We can see stars that are thousands of light years away, galaxies that are millions of light years distant, and the cosmic microwave background from billions of years ago. This visibility connects us to the cosmos, makes us part of something immeasurably vast and beautiful. Yet even in our real universe, we face limitations similar to those in our imagined slow-light cosmos. There are parts of the universe so distant that their light hasn't had time to reach us since the Big Bang. There are events happening right now in distant galaxies that we won't know about for millions of years. We too live in a bubble of visibility, surrounded by a universe that extends beyond our observation. The difference is one of degree, not kind. As you lie there tonight, perhaps gazing out a window at the actual night sky with its thousands of visible stars, consider how different your experience would be if light moved at just 1 mile per hour. The stars you see wouldn't be there. The constellations that humans have used for navigation and storytelling for millennia wouldn't exist. The Milky Way, that river of light across the summer sky, would be invisible. Instead, you would see only darkness punctuated by a few planets, each one showing you its ancient past. And yet, in that darkness, there would be potential. Every moment, photons from distant stars would be infinitesimally closer to arriving. Every second, the universe would be preparing to reveal itself, even if that revelation won't come for billions of years. The darkness wouldn't be empty but pregnant with possibility, filled with light that is always coming, always approaching, always carrying messages from across the cosmos. This is the strange beauty of our slow-light universe, a cosmos where patience isn't just a virtue but a necessity, where the universe reveals itself not all at once but grain by grain over cosmic time, where the night sky is not a display of stars but a canvas of possibility, waiting for light that is always on its way but never quite arrives. It's a universe that teaches us that sometimes the journey is so long that the destination becomes almost mythical, something believed in rather than seen, something that gives meaning to the darkness not through its presence but through its promise. Now we visit our solar system as if wrapped in slow light, with the sun's warmth taking days or weeks to gently wash over each planet, and we begin to truly understand what it means for an entire planetary system to exist in temporal fragments, each world isolated not just by distance, but by the crawling pace of information itself. Picture yourself floating in space, perhaps in some impossible observation post that allows you to survive in the vacuum, watching as light from the sun begins its patient journey outward, spreading like honey poured into the darkness, taking its time to illuminate each planet, moon, and asteroid in turn. The sun itself, that massive fusion reactor at the heart of our solar system, would still be generating energy at its normal rate in this imagined universe. Deep in its core, hydrogen atoms would still be fusing into helium, releasing tremendous amounts of energy. But once that energy begins its journey from the core to the surface, and then from the surface outward into space, everything changes. In our real universe, light from the sun's surface takes about 8 minutes and 20 seconds to reach Earth. In our slow-light cosmos, that same journey would take over 10,000 years. Think about what this means for the fundamental engine of our solar system. The sun would still be shining, still be pumping out energy, but that energy would accumulate in space, creeping outward in an ever-expanding sphere at just 1 mile per hour. Close to the sun, space would be thick with ancient photons, layer upon layer of light from different times, all slowly spreading outward. It would be like a temporal fog of radiation, with photons from today mixing with photons from yesterday, from last year, from last century, all occupying the same region of space but at different stages of their outward journey. Mercury, the innermost planet, orbits at an average distance of about 36 million miles from the sun. In our slow-light universe, sunlight would take about 4,100 years to reach Mercury's orbital distance. But here's where things get even more complex. Mercury isn't stationary. It orbits the sun every 88 Earth days, moving at an average speed of about 105,000 miles per hour. This means Mercury is actually moving 105,000 times faster than the light trying to reach it. The planet would literally be outrunning the sunlight, racing through space faster than the photons that should be warming its surface. Imagine Mercury's strange journey through this slow-light solar system. As it orbits, it would be constantly entering regions of space filled with sunlight from different eras. One moment it might pass through light that left the sun 4,000 years ago, the next moment through light from 4,100 years ago. The planet would experience a bizarre form of time travel, its surface being illuminated by an ever-changing mixture of ancient sunlight from different periods in the sun's history. If the sun had been slightly dimmer 4,000 years ago, and slightly brighter 4,100 years ago, Mercury would experience these variations in rapid succession as it raced through the slowly expanding shells of light. The temperature on Mercury would fluctuate not just from its rotation and its elliptical orbit, as in our universe, but from passing through these different vintages of sunlight. The planet might be baking in intense radiation from a particularly active period of the sun's past, then suddenly cool as it enters a region where the ancient sun had been quieter. These temperature variations would happen on the timescale of Mercury's orbit, days and weeks, even though they reflect solar variations that originally occurred over centuries or millennia. Venus, our sister planet shrouded in thick clouds, orbits at about 67 million miles from the sun. Light would take about 7,600 years to reach Venus's orbit. Like Mercury, Venus moves faster than light in this universe, orbiting at about 78,000 miles per hour. This means Venus too would be sampling different epochs of solar output as it circles the sun, though the variations might be less dramatic than Mercury's due to its greater distance and slower orbital speed. The thick atmosphere of Venus would respond to these varying levels of ancient sunlight in complex ways. The greenhouse effect that makes Venus the hottest planet in our solar system would still operate, but it would be driven by sunlight from nearly 8,000 years ago. The atmospheric dynamics, the sulfuric acid clouds, the super-rotating winds, all would be powered by energy that left the sun before human civilization began. Changes in the sun's output wouldn't affect Venus for millennia, creating a profound disconnect between cause and effect. Earth, our home, orbiting at about 93 million miles from the sun, would receive sunlight that had been travelling for about 10,600 years. This means that the sunlight warming your face on a summer day wouldn't have left the sun recently, or even in recorded history, but during the end of the last ice age, when mammoths still roamed the earth and humans were just beginning to develop agriculture. Every sunrise would be a message from the deep past, every sunset a farewell to ancient light. The implications for Earth's climate would be staggering. Our planet's climate system is driven by solar energy, but in this slow light universe, that energy would be over 10,000 years old by the time it arrives. If the sun were to suddenly dim or brighten today, Earth wouldn't experience the change for over 10 millennia. We would be living on a planet warmed by a star that might no longer exist in the same form, sustained by energy from an epoch we can only study through archaeology. The seasons would still occur due to Earth's axial tilt, but they would be driven by ancient sunlight arriving at different angles. When summer comes to the northern hemisphere, it's not because we're receiving more current sunlight, but because we're receiving more of the sunlight that left the sun 10,600 years ago at a more direct angle. The entire seasonal cycle would be a kind of temporal echo, a pattern preserved in light that has been travelling since before the pyramids were built, before writing was invented, before the first cities were founded. Photosynthesis, the process by which plants convert sunlight into chemical energy, would be running on this ancient light. Every leaf would be a receiver tuned to pick up broadcasts from the sun's distant past. The oxygen we breathe would be produced from sunlight that predates civilization. In a very real sense, life on Earth would be sustained by the past, feeding on temporal fossils of solar energy that have been crawling through space for millennia. Mars, the red planet that has captured human imagination for centuries, orbits at an average distance of about 142 million miles from the Sun. Sunlight would take about 16,200 years to reach Mars. The planet would be illuminated by light from before the last ice age ended, from a time when sea levels were hundreds of feet lower than today, when massive glaciers covered much of North America and Europe. Mars's polar ice caps, composed of water ice and frozen carbon dioxide, would sublime and freeze based on sunlight from this ancient epoch. Dust storms on Mars, which can sometimes engulf the entire planet, would be driven by temperature differentials created by 16,000-year-old solar energy. If we were somehow able to colonize Mars in this slow light universe, we would be living under a sun from humanity's prehistoric past, warming ourselves with photons that began their journey when our ancestors were still learning to paint on cave walls. The asteroid belt, that collection of rocky bodies orbiting between Mars and Jupiter, would be an even stranger environment. Different asteroids at different distances would be illuminated by sunlight from different eras. Ceres, the largest object in the asteroid belt at about 257 million miles from the Sun, would be receiving light that's about 29,000 years old. Smaller asteroids closer to Mars might be lit by 20,000-year-old light, while those closer to Jupiter would be seeing light from 40,000 years ago or more. Mining operations in the asteroid belt, if such things were possible in this universe, would be working in a temporally fragmented environment. An asteroid might be visible in reflected light from 25,000 years ago, but its actual current position would be somewhere else entirely, invisible in the darkness. Spacecraft trying to rendezvous with asteroids would need to navigate not by sight but by calculation, predicting where objects actually are rather than where they appear to be. Jupiter, the giant of our solar system, presents us with even more temporal complexity. At an average distance of 484 million miles from the Sun, Jupiter would receive sunlight that is about 55,000 years old. This light would have left the Sun during the Paleolithic era, when Neanderthals and Denisovans still shared the Earth with our ancestors, when the first musical instruments were being crafted, when humanity was taking its first tentative steps toward behavioral modernity. Jupiter's great red spot, that enormous storm larger than Earth itself, would be driven by atmospheric dynamics powered by this ancient sunlight. The convection patterns that create Jupiter's distinctive banded appearance would be fueled by energy from before written history, before agriculture, before the first permanent human settlements. The 4 Galilean moons, Io, Europa, Ganymede and Callisto, would each be illuminated by this same ancient light, their surfaces reflecting photons that have been travelling since before humans developed language. Io's volcanic activity, the most intense in the solar system, is driven primarily by tidal heating from Jupiter's gravity, rather than solar heating. But the sulfur and sulfur dioxide that erupts from its volcanoes would be visible only in reflected sunlight from 55,000 years ago. The volcanic plumes that can extend hundreds of miles above Io's surface would be illuminated by light older than human civilization, creating a strange juxtaposition of current geological activity, visible only through ancient illumination. Europa, with its subsurface ocean that might harbour life, would be covered in ice that reflects this ancient sunlight. If there is indeed life in Europa's dark ocean, it would exist in a world completely cut off from current solar input, sustained by tidal heating and possibly hydrothermal vents, unaware that the faint sunlight reaching the ice above is a message from the deep past. Any future mission to Europa would need to drill through ice illuminated by 55,000-year-old photons to reach an ocean that has been dark for millions of years. Saturn, with its spectacular ring system, orbits at about 886 million miles from the Sun. Light would take about 101,000 years to reach Saturn, longer than the entire history of Homo sapiens as a distinct species. The sunlight illuminating Saturn's rings would have left the Sun when modern humans were just beginning to migrate out of Africa, when our entire species numbered perhaps just a few thousand individuals. The rings themselves, composed of countless particles of ice and rock, would each reflect this ancient light differently depending on their exact distance from the Sun. The inner rings might be reflecting 100,000-year-old light, while the outer rings reflect light that is 102,000 years old. The delicate structures within the rings, the gaps, the spokes, the braided patterns, would all be visible only through this temporal lens, showing us structures illuminated by light from before human culture existed. Titan, Saturn's largest moon with its thick atmosphere and methane lakes, would be a world shrouded not just in its characteristic orange haze but in temporal mystery. The methane cycle on Titan, with methane rain, rivers and lakes, would be driven by temperature variations caused by 101,000-year-old sunlight. The organic chemistry occurring in Titan's atmosphere, which might resemble the early Earth's, would be powered by photons that predate any human understanding of chemistry or physics. Uranus, tilted on its side and rolling along its orbital path, sits at about 1.8 billion miles from the Sun. Sunlight would take about 205,000 years to reach Uranus. This pale blue-green world would be illuminated by light from before anatomically modern humans evolved, from a time when different human species walked the Earth, when our ancestors were still developing the cognitive abilities that would eventually lead to consciousness as we know it. The extreme seasons on Uranus, caused by its 98-degree axial tilt, would be driven by this ancient sunlight. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. But the sunlight arriving during those long polar days would be from before our species existed. The thin rings of Uranus, discovered only in 1977 in our universe, would be reflecting light older than the human lineage. Neptune, the outermost major planet at about 2.8 billion miles from the Sun, would receive light that is about 318,000 years old. This deep blue world with the fastest winds in the solar system would be driven by energy from before Homo sapiens evolved, from a time when earlier human species were learning to control fire, to make simple tools, to perhaps develop the first glimmers of symbolic thought. The Great Dark Spot on Neptune, similar to Jupiter's Great Red Spot but more transient, would be a storm system powered by ancient thermal gradients. The winds on Neptune, which can reach speeds of 100-200 miles per hour, would be driven by temperature differences created by sunlight that predates human consciousness. Triton, Neptune's large moon orbiting retrograde, would be reflecting this incredibly ancient light, its nitrogen geysers erupting into space illuminated by photons from before our species existed. The Kuiper Belt, that vast region of icy bodies beyond Neptune, would be even more temporally remote. Pluto, at an average distance of 3.7 billion miles from the Sun, would receive light that is about 421,000 years old. The sunlight reaching Pluto would have left the Sun when Homo heidelbergensis roamed the Earth, when the ancestors of both Neanderthals and modern humans were still a single species. The heart-shaped plain on Pluto, discovered by the New Horizons mission Tombaugh Regio, would be illuminated by light 500,000 years old. The nitrogen ice that cycles between Pluto's surface and its thin atmosphere would be driven by temperature variations caused by truly ancient sunlight. Charon, Pluto's large moon, locked in mutual tidal lock with Pluto, would be reflecting the same ancient light, two worlds frozen in a gravitational embrace, illuminated by photons from before human history. Even more distant objects in the Kuiper belt would be receiving progressively older light. Eris, Makemake, Haumea. These distant worlds would be lit by sunlight from 600,000, 700,000, even 800,000 years ago. The scattered disk objects, those bodies with highly elliptical orbits that take them far from the Sun, might receive light that is millions of years old when they reach aphelion, the farthest point in their orbits. The Oort cloud, that hypothetical spherical shell of icy bodies surrounding our solar system at distances of up to a light year or more, would be receiving sunlight so old that it would predate the evolution of our genus. A comet in the Oort cloud, perhaps 1 trillion miles from the Sun, would be illuminated by light that is 114 million years old, light from the Cretaceous period, when dinosaurs still ruled the Earth. When such a comet begins its long fall toward the inner solar system, perhaps disturbed by the gravitational influence of a passing star, it would be leaving a region illuminated by light from the age of dinosaurs and beginning a journey toward light from progressively more recent epochs. As it approaches the Sun, it would travel through shells of progressively younger light, experiencing millions of years of solar history, compressed into its years-long journey. The solar wind, that stream of charged particles flowing outward from the Sun, presents another interesting puzzle in our slow light universe. In our real universe, the solar wind travels at speeds of 300 to 500 miles per second, much slower than light but still incredibly fast. In our slow light universe, the solar wind would actually be travelling 300 to 500 times faster than light. These particles would race past the slowly expanding shells of photons, reaching the planets long before the light that was emitted at the same time. This means that the planets would feel the effects of solar storms and coronal mass ejections thousands of years before seeing them happen on the Sun. Earth's magnetosphere would be buffeted by particles from solar events that wouldn't be visible for another 10,000 years. Auroras would light up the polar skies, driven by solar storms that appear to come from a calm, unchanging Sun. It would be as if the Sun's effects arrived before its causes, a reversal of normal causality that would make space weather prediction impossible. The heliopause, the boundary where the solar wind meets the interstellar medium, would be a region where ancient particles meet ancient light. The Voyager spacecraft, which in our universe have crossed the heliopause and entered interstellar space, would in this slow light universe be travelling through a boundary defined by particles and photons from vastly different epochs. Voyager 1, launched in 1977 and now over 14 billion miles from Earth, would be in a region where sunlight is 1.6 million years old, from long before humans existed. The concept of the habitable zone, that region around a star where liquid water can exist on a planet's surface, would need to be completely reconsidered. In our universe, the habitable zone is determined by the amount of energy a planet receives from its star, which depends on distance and stellar luminosity. But in our slow light universe, planets would be receiving energy from the star as it was thousands or millions of years ago. A star that is gradually brightening, as our Sun is, would have its habitable zone slowly moving outward, but planets wouldn't experience this change for millennia. Earth might currently be in the habitable zone of the Sun, as it was 10,600 years ago, but the current Sun might be too bright or too dim for Earth's current orbit. We would have no way of knowing whether our planet is still in the habitable zone until the light from the present-day Sun finally arrives in 10,600 years. This temporal disconnect between stellar evolution and planetary climate would make the development and maintenance of life extraordinarily precarious. Space exploration in this slow light solar system would be essentially impossible with any technology we can imagine. Spacecraft would disappear into darkness the moment they left Earth, as their reflected sunlight would take years or decades to crawl back to Earth. Mission Control would have no way to track spacecraft visually, depending entirely on other forms of communication that, if they also travel at light speed, would be equally slow. A mission to Mars would involve launching a spacecraft that wouldn't be visible from Earth for years after launch. The spacecraft would arrive at Mars long before Earth could see it get there. The astronauts would land, explore, and potentially return to Earth before anyone on Earth could see their spacecraft reach Mars. It would be like sending explorers into an invisible realm, hoping they succeed but unable to witness their journey. The Mars rovers that have been so successful in our universe would be impossible to operate in a slow light cosmos. Commands from Earth would take thousands of years to reach Mars, and images from the rovers would take thousands of years to return. By the time Earth received the first image from a Mars rover, entire civilizations could have risen and fallen. The rovers would need to be completely autonomous, making all decisions on their own with no possibility of human guidance. The concept of planetary protection, preventing contamination between worlds, would take on new dimensions. If a spacecraft accidentally carried Earth microbes to Mars, we wouldn't see the effects for thousands of years. By the time we observed contamination occurring, it would be ancient history, with potentially irreversible consequences that had been unfolding for millennia. Every action in space would have consequences that wouldn't be visible for thousands or millions of years. As we contemplate this temporally fragmented solar system, we begin to appreciate how profoundly light connects and coordinates the celestial bodies in our actual universe. The relatively fast speed of light allows the solar system to function as a coherent system, with the sun's energy reaching the planets quickly enough to drive their climates and chemistry in something approaching real time. Gravitational effects propagate at light speed, allowing planets to respond to each other's influences within reasonable timeframes. But in our slow light universe, the solar system would be less a system and more a collection of temporally isolated worlds, each one receiving energy from a different epoch of the sun's past, each one invisible to the others except as ancient images crawling through space. It would be a solar system where cause and effect are separated by millennia, where the present is unknowable, and where each world exists in its own temporal bubble. Yet perhaps there would be a strange beauty in this isolation. Each planet would be a world unto itself, pursuing its own destiny unobserved and uninfluenced by current events elsewhere in the solar system. The slow arrival of sunlight would make each photon precious, a message from the deep past that had travelled for millennia to warm a planet's surface or drive its weather. The solar system would be like a cosmic museum, with each planet displaying a different era of solar history, preserved in the light that illuminates it. We gently imagine earthly life adapting to a 1 mile/hour light, where existence itself must reimagine every fundamental assumption about perception, growth, and survival. And you and I together explore how organisms from the smallest bacteria to the largest whales would navigate a world where seeing means waiting, and where the present is always just out of reach. Picture yourself standing in a meadow at dawn in this strange universe, waiting for the sunrise that began hours ago to finally paint the landscape with its ancient light, watching as illumination creeps across the grass blade by blade, flower by flower, each living thing existing in its own moment of receiving the day. In this world, photosynthesis, that fundamental process that sustains most life on Earth, would operate on temporal delays that challenge our understanding of biological efficiency. A leaf on a tree wouldn't receive sunlight instantaneously, but would wait as photons crawl toward it at their leisurely pace. The morning light that appears to strike the eastern side of a tree would actually be light from minutes or hours ago, depending on the distance from the horizon, while the western side remains in darkness that is not shadow, but simply the absence of light that hasn't arrived yet. Consider how a single tree would experience a day in this slow light world. As the Earth rotates, bringing the tree into what should be sunlight, the photons from the sun don't immediately reach the leaves. Instead, light that left the sun 10,600 years ago and has been travelling through space all that time finally completes the last few miles of its journey from the horizon to the tree. The top of the tree, perhaps 50 feet high, would receive this ancient sunlight about 3.5 minutes before the lower branches. The tree would light up gradually from top to bottom, or from one side to the other, depending on the sun's angle. The chloroplasts within each leaf, those cellular factories that convert light into chemical energy, would need to be extraordinarily patient and efficient. They might receive bursts of photons as waves of light finally arrive, followed by periods of darkness as they wait for the next wave. Perhaps plants in this universe would evolve different photosynthetic strategies, maybe storing incoming light energy more efficiently, or developing ways to predict when light will arrive based on other cues. The circadian rhythms that govern so much of life on Earth would be profoundly different. In our world, organisms from cyanobacteria to humans have internal clocks synchronized to the 24-hour day-night cycle. But if light takes hours to cross a landscape, when exactly does day begin? A flower that opens with the sunrise might begin opening when it detects the warmth of infrared radiation, which would also travel at 1 mile per hour, or perhaps in response to the solar wind particles that would actually arrive faster than light in this universe. Flowers that track the sun across the sky, like sunflowers, would face an impossible task. The sun they see wouldn't be where the sun actually is, but where it was hours ago, depending on its height in the sky. By the time light from the noon sun reaches a sunflower, the actual sun has already moved significantly toward the western horizon. Perhaps these plants would evolve to predict the sun's motion, rather than track it directly, using internal timers to anticipate where the sun will appear to be, or perhaps they would abandon solar tracking altogether in favor of other strategies. The very colors of life would tell a different story in this slow light world. The green of chlorophyll, the reds and yellows of flower petals, the iridescent blues of butterfly wings. All these colors exist because of how biological molecules interact with specific wavelengths of light. But if light moves so slowly, would these color-based strategies still evolve? A red flower attracts pollinators in our world because its red petals are immediately visible to insects with the right visual systems. But if the red light reflecting from the petals takes seconds or minutes to reach a nearby bee, would this signaling system still work? Perhaps life would evolve to use other forms of communication that don't depend on light. Chemical signals would become even more important than they already are. Pheromones drifting on the wind might be the primary means of communication between organisms. Sound would be king in this universe, travelling at 767 miles per hour through air, far faster than light's sluggish 1 mile per hour. Birds might evolve elaborate songs not just for mating and territory, but for echolocation, navigating a world where vision provides only delayed information. The evolution of eyes presents a fascinating puzzle in our slow light universe. In our world, eyes evolved because light provides nearly instantaneous information about the environment. A predator can see prey and strike in fractions of a second. Prey can detect threats and flee immediately. But if light crawls along at 1 mile per hour, would eyes ever evolve at all? What advantage would there be in seeing something as it was seconds, minutes, or hours ago? Perhaps eyes would evolve but function very differently. Instead of providing real-time information, they might serve as historical records, allowing organisms to build up mental maps of their environment over time. An animal might use its eyes to observe where things were and use that information to predict where things are now. The visual cortex might be less about processing current images and more about extrapolating from past images to construct models of the present. Predator-prey relationships would be transformed beyond recognition. A hawk circling overhead wouldn't be able to see a mouse in real time. By the time light from the mouse reaches the hawk's eyes, the mouse has moved. The hawk would need to predict where the mouse is based on where it was, calculating trajectories and probabilities rather than simply seeing and striking. Perhaps predators would rely more on vibration, smell and sound, or perhaps they would evolve entirely different hunting strategies we can't imagine. Consider a lion hunting on the African savanna in this slow light world. The lion sees a herd of zebras, but the image is from minutes ago when the herd was hundreds of meters away. The zebras have been moving since then, but their current position is invisible. The lion must somehow determine where the zebras are now, perhaps by listening to their hoofbeats, smelling their scent on the wind, or using some other sense we don't possess. The hunt becomes less about speed and reflexes and more about prediction and positioning. The zebras, meanwhile, face their own challenges. They see the lion where it was minutes ago, not where it is now. Their famous stripes, which in our world may confuse predators by making it hard to single out individuals in a moving herd, might serve a different purpose or might not evolve at all. Perhaps instead of visual camouflage, prey animals would evolve acoustic camouflage, ways to mask the sounds of their movement or breathing. Marine life would face unique challenges and opportunities in this slow light ocean. Water absorbs light even in our universe, with sunlight barely, penetrating beyond a few hundred meters. In a slow light ocean, the depths would be even darker, with sunlight taking hours or days to filter down through the water column. Each meter of depth would represent additional minutes or hours of delay, creating temporal layers in the ocean where different depths exist in different moments of the past. Bioluminescence, the production of light by living organisms, would take on new significance. In our world, a deep-sea fish can flash a light and immediately see the response. But if that light travels at only 1 mile per hour, the flash would expand outward slowly, illuminating the surrounding water gradually. A predator using bioluminescence to hunt would need to wait for its light to reach prey and for the reflected light to return. Perhaps bioluminescent organisms would produce continuous glows rather than flashes, creating slowly expanding spheres of light in the darkness. Coral reefs, those diverse ecosystems that depend on photosynthetic algae living within coral polyps, would need to adapt to the slow arrival of sunlight. The zooxanthellae algae that provide nutrients to coral through photosynthesis would receive sunlight that had been filtered through water for hours, arriving in slow pulses as waves on the surface create moving patterns of light and shadow. The daily cycle of photosynthesis and respiration that drives reef productivity would be stretched and distorted. Migration patterns would need to account for the temporal nature of visual navigation. Birds that navigate by the sun would need to calculate not where the sun appears to be, but where it actually is. Monarch butterflies travelling thousands of miles would be following a sun that appears to be in the wrong position, its image lagging behind its actual location by hours. Perhaps magnetic navigation would become dominant, or perhaps organisms would evolve internal maps that don't depend on visual cues. The human settlement patterns and urban development would be fundamentally different in this slow light world. Cities couldn't sprawl as they do in our world, because visual communication across distances would be impossible. A traffic light a block away would be showing its state from minutes ago. Drivers would need to predict what the light will be when they arrive, not what it appears to be now. Perhaps cities would be organized into small, dense clusters, with minimal visual interaction between clusters. Architecture would evolve to account for the slow propagation of light. Buildings might be designed with internal courtyards and light wells that minimize the distance light needs to travel. Windows would be less about views and more about allowing light to enter from the shortest possible distance. The famous skylines of cities like New York or Hong Kong would never develop because tall buildings would be visually isolated from their surroundings, their upper floors existing in a different temporal zone from the street level. Street lighting would create slowly expanding bubbles of illumination. When a streetlight turns on at dusk, it wouldn't immediately light the street but would create an expanding sphere of light crawling outward at 1 mile per hour. Pedestrians would watch these spheres of light slowly engulf the sidewalk, providing illumination that lags behind the actual position of the lamp. Walking down a street at night would be like moving through a series of overlapping temporal zones, each lamp illuminating the space around it as it was seconds or minutes ago. Indoor lighting would be equally strange. When you flip a light switch, the bulb would turn on immediately, but the light would take time to fill the room. You would watch as illumination crawls across the floor and up the walls, taking several seconds to reach the far corners. Reading a book would require waiting for light from your lamp to reach the pages, and then for the reflected light from the pages to reach your eyes. Perhaps people would develop habits of turning lights on well before they need them, anticipating the delay. Agriculture would need to be completely reimagined. Farmers couldn't observe their fields in real time, seeing crops as they were minutes or hours ago depending on the size of the field. Pest infestations or disease outbreaks would be invisible until their effects had been spreading for some time. Perhaps farming would become more predictive, based on models and sensors rather than visual observation. Or perhaps fields would be much smaller, allowing farmers to stay within a reasonable light delay distance of their crops. Greenhouses would take on new importance as controlled environments where light distances could be minimized. But even in a greenhouse, the delay between the grow lights and the plants would need to be considered. Perhaps plants would be arranged in vertical towers with lights interspersed among them, minimizing the distance light needs to travel. Or perhaps artificial lights would be pulsed in patterns that account for the propagation delay, ensuring that all plants receive synchronized illumination. The food chain itself would be restructured around the slow speed of light. Photosynthetic organisms would still form the base, but they would be operating on ancient sunlight, converting 10,600-year-old photons into chemical energy. Herbivores eating these plants would be consuming energy captured from truly ancient sunlight. Carnivores eating herbivores would be even further removed from the original solar source. The entire ecosystem would be running on a massive temporal delay, powered by energy from before human civilization began. Human social interactions would be profoundly affected by slow light. Face-to-face conversations would involve a slight but noticeable delay. When talking to someone across a dinner table, you would see their expressions from a fraction of a second ago, their lips moving out of sync with their words. Perhaps people would learn to focus on audio rather than visual cues, or perhaps new social norms would develop that account for these delays. Video calls would be impossible over any significant distance. A call between two people in the same city but different neighbourhoods might involve minutes of delay. You would speak to someone and not see their reaction for several minutes, by which time the conversation would have moved on. Perhaps communication would revert to written messages or audio recordings, with visual communication reserved for people in the same room. Television and movies would exist, if at all, as purely local phenomena. A television broadcast would take hours to cross a city, days to cross a country. By the time a signal reached distant viewers, it would be showing old news. Perhaps each neighbourhood would have its own television station, broadcasting only to nearby homes. Or perhaps visual entertainment would be replaced by radio dramas and podcasts, taking advantage of sound's relative speed advantage. Photography would become an art of patience and prediction. Taking a portrait would involve waiting for light to travel from the subject to the camera. A photographer might need to anticipate expressions and movements, clicking the shutter before the desired moment appears in the viewfinder. Group photos would be particularly challenging, with people at different distances appearing to be from different moments in time. Perhaps photography would evolve into a more abstract art form, embracing the temporal distortions rather than trying to capture single moments. Sports would need to be completely reconceptualized. In our world, sports often involve split-second reactions to visual stimuli. A baseball batter sees the pitch and swings in a fraction of a second. A tennis player sees the ball coming and moves to intercept it. But if light moves at only 1 mile per hour, these visual reaction sports would be impossible. The ball would arrive long before its image does. Perhaps sports would evolve to be more strategic and less reactive. Games might involve predicting trajectories based on sound or other cues, or perhaps entirely new sports would develop that take advantage of the slow speed of light. Imagine a game where players must predict where objects will be based on where they appear to be, with scoring based on accurate prediction rather than quick reflexes. Education would need to account for the temporal complexity of perception. Children would learn from an early age that what they see is not the present, but the past. Mathematics and physics would include extensive training in calculating actual positions from apparent positions. Biology classes would teach about ecosystems that function across multiple temporal zones. History would include not just human history but the history of the light itself, when the sunlight illuminating the classroom actually left the sun, what Earth was like when that happened. Art would likely embrace the temporal nature of vision in this universe. Painters might create works that are meant to be viewed from specific distances, with different parts of the painting becoming visible at different times as light propagates from the canvas to the viewer. Sculptors might create pieces that reveal themselves gradually as light crawls across their surfaces. Performance art might involve choreographed movements that account for the delay between action and perception. Music might become the dominant art form, taking advantage of sound's speed advantage over light. Concerts would be primarily acoustic experiences, with the visual element delayed and distorted. Musicians might not even try to synchronize their movements with their music for distant audience members, accepting that the visual and audio experiences would be separate. Or perhaps new forms of music would develop that intentionally play with the disconnect between sight and sound. The concept of privacy would be completely different. Closing curtains or doors would only prevent new light from escaping, but light that had already left would continue its slow journey outward. Your actions would remain visible through windows for seconds or minutes after you've closed them. Perhaps buildings would be designed with airlocks of darkness, multiple layers of barriers to prevent light from escaping. Or perhaps privacy would be redefined, with people accepting that their past actions remain visible even after they've moved on. Mental health and psychology would need to account for the strange perceptual environment. Humans would grow up in a world where they can never see the present, where every visual perception is delayed, where cause and effect are temporally separated. This might lead to different cognitive patterns, different ways of understanding reality. Perhaps humans would be naturally better at prediction and modelling, having evolved in an environment where these skills are essential for survival. The development of technology would follow different paths. Without the ability to see immediate results, inventors and engineers would need to work more theoretically. You couldn't simply build something and see if it works. You would need to wait for the light from your creation to reach your eyes. Perhaps technological development would be slower but more thoughtful, with more emphasis on calculation and prediction rather than trial and error. Computers and electronics would face unique challenges. In our world, computer monitors update dozens of times per second, creating the illusion of smooth motion. But if light travels at only 1 mile per hour, the light from each pixel would take time to reach the viewer's eyes. A monitor might update, but you wouldn't see the change for seconds. Perhaps displays would need to predict what users want to see and update in advance, or perhaps visual interfaces would be abandoned in favor of audio or tactile feedback. The internet, if it could exist at all, would be fundamentally different. Data transmitted as electromagnetic signals would crawl along at 1 mile per hour. Downloading a web page from a server in the same building might take minutes. Accessing information from another city could take hours or days. Perhaps networks would be extremely localized, with each neighborhood having its own isolated internet. Or perhaps information would be physically transported on storage devices, with data couriers carrying hard drives from place to place faster than electromagnetic signals could travel. Manufacturing and industry would need to account for the slow speed of light. Quality control based on visual inspection would be difficult when you're seeing products as they were seconds or minutes ago. Assembly lines would need to operate on prediction rather than observation. Perhaps manufacturing would become more distributed, with small facilities producing goods locally rather than large factories trying to coordinate operations across great distances. Transportation would be one of the few areas where technology might advance similarly to our world, since vehicles don't depend on light to move. But navigation would be completely different. You couldn't use visual landmarks for navigation, because they would show you where you were, not where you are. GPS would be impossible since satellite signals would take years to reach Earth. Perhaps navigation would rely on dead reckoning, inertial guidance, or following physical paths like roads and railways. Emergency services would face extraordinary challenges. A fire department receiving a call about a fire wouldn't be able to see the fire until they were very close to it. The smoke and heat would arrive before the visual confirmation. Firefighters would need to operate based on thermal sensors and other non-visual cues. Medical emergencies would be even more challenging, with EMTs unable to visually assess patients until they're within a few feet. Weather forecasting would be both easier and harder. Easier because weather systems would move faster than light, allowing their effects to be felt before they're seen. You would experience rain while the sky still appears clear, feeling the storm that you won't see for hours. But harder because gathering visual data about weather patterns would be nearly impossible. Satellite imagery would be useless, showing weather from years ago. Perhaps weather prediction would rely on networks of ground-based sensors measuring pressure, temperature, and humidity. As we contemplate life in this slow light world, we see how fundamentally light shapes not just vision, but every aspect of existence. Life as we know it evolved in a universe where light is fast enough to provide useful real-time information about the environment. Slow that light down to a walking pace, and every biological system, every behavior, every survival strategy would need to be reconsidered. Here we sit with the scientists of this slow light cosmos, watching how they test, measure, and quietly wonder about a universe where light strolls instead of sprints, and we discover together how the entire edifice of scientific knowledge would need to be rebuilt from first principles when the fundamental messenger of information crawls through space at just 1 mile per hour. Imagine yourself in a laboratory where every experiment takes not minutes or hours, but potentially years to complete, where the simple act of observation becomes an exercise in patience that spans generations, and where scientists must be more like architects of time, building experiments that their grandchildren will finally see the results of. The scientific method itself would need to be reconsidered in this universe. In our world, we observe, hypothesize, experiment, and observe the results, often within short time frames. But when light travels so slowly, observation becomes temporally complex. You might set up an experiment and not be able to see the results for hours, days, or even years, depending on the scale. A chemist mixing reagents in a beaker would need to wait for the light from the reaction to reach their eyes. By the time they see the color change indicating a reaction has occurred, the reaction itself is already complete, and the products may have already degraded or reacted further. Consider a simple physics experiment, measuring the speed of a falling object. In our universe, we can use high-speed cameras to track an object's descent, capturing thousands of frames per second. But in a slow light universe, the light from the falling object would be crawling toward the camera. By the time the image of the object at the top of its fall reaches the camera, the object has already hit the ground. The camera would record not the fall itself, but a temporal smear, with the object appearing to be in multiple positions simultaneously, as light, from different moments of its fall, arrives at the same time. Perhaps scientists would develop new methods of measurement that don't rely on light. Pressure sensors, accelerometers, and other devices that measure physical properties directly would become the primary tools of investigation. Or perhaps they would embrace the temporal nature of their observations, developing mathematical frameworks that account for the delay between event and observation. Every equation would include terms for the propagation time of light, turning simple calculations into complex temporal puzzles. Chemistry would be particularly challenging in this slow light world. Chemical reactions often happen in fractions of a second, with bonds breaking and forming faster than the eye can see, even in our universe. But if light moves at only 1 mile per hour, observing these reactions visually would be impossible. A reaction that takes a millisecond to occur would be invisible until the light from it finally reaches the observer's eyes seconds later. By then, the products might have undergone further reactions, decomposed, or evaporated. Chemists might rely entirely on non-visual methods of analysis. Mass spectrometry, which measures the mass of molecules, would still work, though the electromagnetic fields used to manipulate ions would propagate slowly. Chemical sensors that detect specific molecules through direct contact would become essential. Perhaps chemistry would develop along different lines entirely, focusing on reactions slow enough to be observed, or on theoretical predictions rather than direct observation. The periodic table might still be discovered, but through different means. In our universe, elements were identified partly through their emission spectra, the specific colours of light they emit when excited. But if light travels so slowly, spectroscopy would be nearly impossible. The light from an excited atom would take so long to reach a detector that the atom would have long since returned to its ground state. Perhaps elements would be identified through their chemical properties alone, or through some other characteristic we haven't discovered because we've always had spectroscopy available. Biology would face its own unique challenges. Microscopy, essential to our understanding of cells and microorganisms, would be severely limited. Light from a specimen would take time to travel through the microscope to the observer's eye. A bacterium swimming across a microscope slide would be invisible in real time, its image arriving after it had already completed its journey. Perhaps biologists would develop techniques to slow down biological processes to match the speed of light, cooling specimens to near freezing to reduce molecular motion. The discovery of DNA structure would likely happen differently, if at all. In our universe, X-ray crystallography revealed the double helix structure, with X-rays diffracting through crystallized DNA to create patterns that could be interpreted. But X-rays are electromagnetic radiation, traveling at the speed of light. In our slow light universe, X-ray crystallography would take so long that the crystals might degrade before the diffraction pattern could be recorded. Perhaps scientists would discover DNA structure through chemical analysis alone, or perhaps the structure would remain a mystery. Evolution by natural selection might still be discovered, but the evidence would be different. Darwin's finches, with their varied beak shapes adapted to different food sources, would still exist. But observing them would be challenging when you see each bird as it was seconds ago, not as it is now. Perhaps evolutionary biology would rely more on fossil evidence and comparative anatomy, building theories from static specimens rather than living observations. Ecology would need to account for the temporal fragmentation of ecosystems. When observing a forest, an ecologist would see each organism as it was at a different time in the past, depending on its distance. A bird in a nearby tree would appear as it was seconds ago, while a deer in a distant meadow would appear as it was minutes ago. Understanding ecological interactions would require complex mathematical models that account for these temporal offsets. Physics would be revolutionized in ways we can barely imagine. Einstein's special and general relativity, which depend on the speed of light being constant and finite, would need to be reformulated for a universe where light crawls along at 1 mile per hour. The relationship between space and time would be different. Time dilation and length contraction would occur at much lower velocities. You wouldn't need to approach the speed of light to experience relativistic effects. Walking speed would be a significant fraction of light speed. The equation E mc2 would have dramatically different implications. with c, the speed of light, being only 1 mile per hour instead of 186,282 miles per second. The energy contained in matter would be vastly reduced. Nuclear reactions might not be possible, or might work completely differently. The sun might not be able to shine through fusion, requiring us to imagine entirely different energy sources for stars. Quantum mechanics would face its own challenges. The uncertainty principle, wave-particle duality, and quantum entanglement all involve the behavior of particles and waves at the smallest scales. If photons travel at only 1 mile per hour, would quantum effects be observable at larger scales? Would the wave nature of light be more apparent when you can watch individual photons slowly traversing space? Perhaps quantum mechanics would be discovered earlier in scientific history, its effects being more obvious in everyday life. The famous double-slit experiment, which demonstrates the wave-particle duality of light, would take on a different character. Instead of photons passing through the slits and creating an interference pattern almost instantaneously, you would wait and watch as individual photons slowly make their way through the apparatus. The interference pattern would build up not over milliseconds but over hours or days. Scientists could potentially track individual photons through the experiment, which might resolve some of the mysteries of quantum mechanics or create entirely new ones. Astronomy, as we discussed in earlier chapters, would be primarily theoretical rather than observational. Unable to see stars or galaxies, astronomers would need to infer the structure of the universe through other means. Perhaps they would detect gravitational effects from distant masses, building models of invisible stars and galaxies based on their influence on local space-time. Or perhaps they would develop theories about the universe that don't include stars at all, imagining a cosmos very different from our own. The discovery of gravitational waves would be crucial in this universe. In our world, LIGO detected gravitational waves in 2015, confirming a prediction of Einstein's general relativity. These waves travel at the speed of light, so in our slow light universe, they would also propagate at 1 mile per hour. But they would still exist, ripples in space-time itself crawling outward from massive accelerating objects. Perhaps gravitational wave astronomy would be the primary way of studying the distant universe, with scientists waiting patiently for waves from cosmic events to slowly wash over Earth. Particle physics would develop along different lines. Particle accelerators like the Large Hadron Collider accelerate particles to near light speed to create high-energy collisions. But if light speed is only 1 mile per hour, reaching near light speed would be trivial. A bicycle could travel faster than light in this universe, if that were physically possible. Perhaps particle physics would focus on different phenomena, or perhaps the fundamental nature of particles themselves would be different in a universe with such a slow speed of light. The search for dark matter and dark energy would be even more challenging than in our universe. These mysterious components of the cosmos are already invisible to us, detected only through their gravitational effects. In a slow light universe, with even normal matter difficult to observe at a distance, dark matter would be even more elusive. Perhaps scientists would develop entirely different cosmological models that don't require dark matter. Or perhaps they would accept that most of the universe is fundamentally unknowable. Mathematics might become even more central to science than it already is. Unable to rely on direct observation for many phenomena, scientists would need to build elaborate mathematical models to predict and understand the universe. Theoretical physics would dominate over experimental physics. Scientists might be more like philosophers, using logic and mathematics to deduce the nature of reality rather than observing it directly. Computer simulations would be essential tools, perhaps the only way to visualize phenomena that can't be directly observed. A computer could calculate where objects actually are based on where they appear to be, creating real-time models of the present that no one can actually see. Virtual reality might not be for entertainment, but for scientific visualization, allowing scientists to experience a simulated version of the present rather than the delayed past they actually perceive. The development of technology would be slow and methodical. Engineers couldn't simply build something and see if it works. They would need to wait for light from their creation to reach their eyes. Rapid prototyping would be impossible. Perhaps engineering would be more theoretical, with designs thoroughly tested in simulation before being built. Or perhaps engineers would rely on tactile and auditory feedback, feeling and listening to their machines rather than watching them. Telecommunications would be perhaps the greatest technological challenge. In our world, we've built a global communications network based on electromagnetic signals traveling at light speed. But if those signals travel at only 1 mile per hour, global communication becomes impossible on human timescales. A phone call across an ocean would involve delays of months or years. The internet as we know it couldn't exist. Perhaps communication technology would develop along completely different lines. Maybe scientists would discover some phenomenon that travels faster than light in this universe. Perhaps gravitational waves, or some form of quantum entanglement that allows instantaneous communication. Or perhaps society would simply accept that long-distance communication is impossible, developing strong local communities that rarely interact with distant ones. Medicine would be profoundly affected by the slow speed of light. Many diagnostic tools rely on electromagnetic radiation, X-rays, MRI, CT scans. If these forms of radiation travel at only 1 mile per hour, medical imaging would take hours or days. A patient would need to remain perfectly still while X-rays slowly propagate through their body and then crawl toward the detector. Perhaps medicine would rely more on chemical tests, physical examination, and predictive models based on symptoms rather than imaging. Surgery would be particularly challenging. Surgeons typically rely on their vision to guide their work, but if light from the surgical field takes seconds to reach their eyes, they would be operating on the past, not the present. Perhaps surgery would become more robotic, with computer systems predicting the current state based on delayed visual information. Or perhaps surgeons would operate primarily by touch, developing extraordinary tactile sensitivity. Materials science would need new methods of analysis. Electron microscopes, which use beams of electrons instead of light, would face the same speed limitations if electrons are limited to 1 mile per hour. Studying the structure of materials at the atomic level would be nearly impossible through direct observation. Perhaps scientists would rely on bulk properties, strength, conductivity, magnetism, to infer atomic structure, building models without ever seeing atoms directly. Environmental science would face unique challenges in monitoring and understanding Earth systems. Satellite observation would be impossible, with electromagnetic signals taking years to travel from orbit to Earth. Weather patterns, ocean currents, and atmospheric changes would need to be studied through ground-based sensors. Climate science might develop differently, perhaps focusing more on local and regional patterns rather than global systems. The study of consciousness and neuroscience would take on new dimensions. If neural signals are electrical, and electricity is limited by the speed of light, then neural signals would propagate at only 1 mile per hour through the brain. Thoughts would unfold slowly, with signals taking seconds or minutes to travel from one brain region to another. Perhaps consciousness in this universe would be fundamentally different, a slow, deliberate process rather than the rapid stream we experience. Agricultural science would need to develop new methods for crop monitoring and improvement. Farmers couldn't visually inspect their fields in real time, seeing plants as they were minutes or hours ago. Plant breeding programs that rely on observing traits would be challenging when you can't see the current state of the plants. Perhaps agriculture would become more automated, with sensors and predictive models replacing visual observation. Forensic science would be transformed. Crime scene investigation typically relies heavily on visual evidence, photographs, video surveillance, eyewitness accounts. But if light travels slowly, security cameras would show events from minutes or hours ago, not the present. Eyewitnesses would have seen events as they were, not as they are. Perhaps forensics would rely more on physical evidence, fingerprints, DNA, chemical traces that can be collected and analysed without depending on light. The philosophy of science itself would be different in this slow light universe. The relationship between observation and reality, already complex in our world, would be even more fraught. Scientists would need to accept that they can never observe the present, only the past. Every measurement would be a historical record. The concept of simultaneity, already relative in Einstein's universe, would be even more fluid. Scientists might develop new philosophical frameworks for understanding a reality that can never be directly observed in its current state. Education in the sciences would need to account for this temporal complexity from the beginning. Children would learn that observation always involves delay, that seeing is not believing but remembering. Science textbooks would include chapters on temporal calculation, teaching students how to work backwards from observations to determine when events actually occurred. Laboratory exercises would include waiting periods, teaching patience as a scientific virtue. Scientific collaboration would be challenging across distances. Researchers in different cities or countries couldn't share visual data in real time. A scientist in New York couldn't show a colleague in Los Angeles the results of an experiment until hours or days after it was completed. Perhaps scientific communities would be highly localized, with research groups clustered in small geographic areas. Or perhaps scientists would develop new forms of collaboration that don't depend on visual communication. The peer review process would be different. Scientific papers would need to describe experiments and results that can't be visually verified by reviewers. Perhaps there would be more emphasis on mathematical proofs and logical arguments rather than experimental evidence. Or perhaps experiments would be designed to produce physical artifacts that can be shipped to reviewers rather than images that would take too long to transmit. The concept of scientific reproducibility would be complex. Reproducing an experiment would mean not just performing the same procedures, but accounting for all the temporal delays involved. Two scientists performing the same experiment might get different results simply because they observed the results from different distances, introducing different delays. Scientific papers would need to specify not just what was done, but when and from where it was observed. Funding for science would require extreme patience from society. A research project might take decades or centuries to produce observable results. Governments and institutions would need to commit resources to investigations that won't bear fruit for generations. Perhaps science would be seen as a multi-generational endeavour, with families of scientists passing research projects down through the generations like heirlooms. The history of science in this universe would be a story of patient accumulation rather than sudden breakthroughs. There would be no eureka moments of immediate discovery, but slow realizations building over years or decades. Scientific revolutions would unfold over centuries rather than years. Perhaps scientists would be revered not for their individual discoveries, but for their contributions to multi-generational research programs. As we contemplate science in this slow light universe, we see how fundamentally the speed of light shapes not just what we can know, but how we can know it. Science as we understand it depends on the ability to observe, to see causes create effects, to watch phenomena unfold. Slow light to a crawl, and the entire scientific enterprise must be reimagined. Scientists would be like archaeologists of the present, always digging through layers of time to understand what's happening now. Yet, perhaps, there would be advantages to this slow science. Without the pressure for immediate results, scientists might think more deeply, plan more carefully. Theories would need to be more robust, able to make predictions that won't be verified for years. The pace of scientific progress might be slower, but it might also be more thoughtful, more careful, less prone to errors that come from rushing to publish. In this patient universe, science would be less about discovery and more about prediction. Scientists would be building models of a present they can't see, inferring the current state of the universe from observations of its past. It would be a science of shadows and echoes, of traces and implications, and perhaps, in learning to understand a universe they can never quite see, these scientists would develop insights into the nature of reality that we, with our relatively fast light, have missed. The slow light universe would teach us that science is not just about observation, but about imagination, not just about seeing, but about reasoning, not just about discovering what is, but about inferring what must be. It would be a universe where the greatest scientific tool is not the telescope or microscope, but the human mind, capable of reaching beyond the limitations of slow light to grasp truths that can't be directly observed. Now we think about communication, signals whispered across oceans, between planets, and perhaps someday between stars, all moving at 1 mile per hour through the dark, and we discover together how the fundamental human need to connect and share transforms when every message becomes a journey through time as well as space. You imagine sending a message to a friend far away, knowing that your words will travel like a gentle caravan of light, arriving as a future gift. And in this contemplation, we find something profound about patience, about the faith required to speak into the darkness, knowing your voice won't be heard for days, years, or even lifetimes. In this slow light universe, the simple act of communication becomes an exercise in temporal navigation. When you speak to someone across a room, your words travel through the air at the speed of sound, about 767 miles per hour at sea level, arriving far faster than your image. They hear you almost immediately, but they see your lips moving seconds later, creating a disconnect between audio and visual that would define every conversation. Perhaps people would learn to close their eyes when listening, to avoid the confusion of watching lips move out of sync with words. Or perhaps the brain would adapt, learning to automatically account for the delay. Consider a conversation between two people sitting at opposite ends of a dinner table, perhaps 10 feet apart. Your words reach your dining companion in about 0.09 seconds, essentially instantaneous to human perception. But the light carrying your image takes about 7 seconds to cross those 10 feet. Your companion hears you say, "Please pass the salt immediately," but sees you mouth those words 7 seconds later, long after they've already handed you the salt shaker. Every meal becomes a temporal puzzle, with actions and reactions separated by the crawling pace of light. The development of language itself might follow different evolutionary paths in such a universe. In our world, much of communication is nonverbal. Facial expressions, hand gestures, body language all supplement our words. But if these visual cues arrive seconds or minutes after the words they're meant to accompany, would they still evolve as part of communication? Perhaps language would become more precise, more complete in its audio form alone, without relying on visual supplements. Or perhaps entirely new forms of communication would develop, using sound patterns or vibrations that can travel faster than light. Written communication would take on extraordinary importance in this world. A letter, once written, exists as a physical object that can be carried from place to place faster than light could carry its image. A messenger on horseback travelling at 20 miles per hour would be moving 20 times faster than light. They could deliver a written message between towns in hours, while a light signal would take days. Perhaps civilization would develop around physical message networks, with riders, ships, and eventually trains carrying information faster than electromagnetic signals ever could. The postal service would be not just convenient but essential for any communication beyond shouting distance. Every town might have multiple mail deliveries per day, with letters moving between neighbourhoods faster than phone calls could travel if phones were even possible. The written word would be king, with literacy being not just valuable but necessary for participation in society. Books and newspapers would be the primary means of mass communication, with printing presses being more important than any electromagnetic technology. But let's dream for a moment about what electromagnetic communication might look like in this universe, despite its limitations. Radio waves, travelling at the same 1 mile per hour as light, would crawl across the landscape. A radio station broadcasting from the centre of a city would take hours for its signal to reach the suburbs. By the time the morning news reached listeners 10 miles away, it would be afternoon. Every broadcast would be old news by the time it arrived. Perhaps radio would still develop, but for different purposes. Instead of live broadcasting, radio stations might transmit continuous loops of information, updated daily or weekly. Listeners would tune in knowing they're hearing information from hours or days ago, treating radio more like a slow-moving newspaper than a source of current information. Emergency broadcasts would be useless for immediate threats, but might warn of slowly developing situations like approaching storms or gradual floods. Television, if it existed at all, would be even more limited. The complexity of transmitting moving images at 1 mile per hour would make live television impossible. Perhaps television would be more like a visual newspaper, broadcasting still images with audio narration. Or perhaps the technology would never develop at all, with society finding other forms of entertainment and information distribution. The telephone presents an interesting thought experiment. If electrical signals travel at the speed of light, then telephone signals would also crawl along at 1 mile per hour. A phone call to someone 1 mile away would involve a 2-second delay each way, noticeable, but perhaps manageable. But a call to someone 10 miles away would involve a 20-second delay each way. You would speak, then wait 20 seconds to hear their response, which would be to something you said 40 seconds ago. Conversations would be impossible in any natural sense. Perhaps telephone technology would evolve differently, more like voicemail or recorded messages. You might record a message, send it through the phone lines, and then wait for a recorded response. Phone conversations would be asynchronous, stretched out over hours or days, or perhaps phones would only be used for very local communication, within neighbourhoods or buildings where the delays are manageable. The internet, that global network that defines so much of modern life, could not exist in anything resembling its current form. Data packets travelling at 1 mile per hour would take years to cross oceans. A web page hosted in London would take months to load in New York. Email to another continent would be slower than postal mail. The idea of a global interconnected network would be impossible. Instead, perhaps each city or region would have its own isolated network, a local internet that serves only nearby users. Information would be physically transported between these networks on storage devices, hard drives carried by train or ship, updating local networks with information from distant ones. It would be like the early days of computing, when magnetic tapes were shipped between facilities, but on a permanent basis because electromagnetic communication would never get faster. Social media, if it could exist at all, would be profoundly different. You couldn't have real-time interactions with people beyond your immediate vicinity. Perhaps social media would be more like collaborative journalism, with people contributing to slowly evolving documents that spread physically from place to place. Or perhaps the concept wouldn't develop at all, with social interaction remaining primarily face-to-face within local communities. Now let's expand our view beyond Earth and consider interplanetary communication. We discussed earlier how the planets of our solar system would be temporally isolated, each one visible only as it was years or millennia ago. Communication between planets would be even more challenging. A radio signal from Earth to Mars would take between 3,900 and 28,000 years to arrive, depending on the planet's relative positions. A conversation between Earth and Mars would span longer than all of recorded human history. If humanity somehow developed space travel in this universe, colonies on other planets would be completely isolated. A Mars colony couldn't communicate with Earth in any meaningful way. They would be on their own, developing their own culture, their own technology, their own destiny, with no way to share their experiences with Earth until millennia had passed. Each planet would be its own island of humanity, separated not just by space, but by insurmountable delays in communication. Perhaps interplanetary civilization would develop through physical travel rather than communication. Generation ships might carry not just people, but information between worlds. These ships, travelling faster than light, since light is so slow in this universe, would be the only connection between planetary civilizations. They would arrive at Mars carrying news from Earth that, while years old due to travel time, would still be more recent than any electromagnetic signal. The search for extraterrestrial intelligence, SETI, would be essentially impossible in this universe. In our world, we search for radio signals from alien civilizations, hoping to detect broadcasts from distant stars. But if radio waves travel at only 1 mile per hour, a signal from the nearest star would take billions of years to reach us. Even if the galaxy were teeming with broadcasting civilizations, we would never know. Their signals would still be crawling through interstellar space, not due to arrive for eons. First contact with an alien civilization, if it ever happened, would have to be physical. Aliens would need to actually travel to Earth, arriving in person rather than announcing themselves through electromagnetic signals. And once here, communication with their homeworld would be impossible. They would be permanent emigrants, cut off from their origins by the slow speed of light. Every interstellar journey would be a one-way trip, not just in terms of travel, but in terms of communication. The concept of memory takes on new significance in this slow-light universe. In our world, we can document events with photography and video, creating records that can be instantly shared and preserved. But when light moves so slowly, documentation becomes complex. A photograph takes time to capture as light crawls from the subject to the camera. A video would be a series of temporal smears, each frame containing light from different moments. Perhaps memory, human memory, would be more valued in this universe. Without reliable visual documentation, eyewitness accounts would be crucial. People might develop stronger memory skills, learning to remember details that in our world we would simply photograph. Oral history would be more important than recorded history. Stories passed down through generations would be the primary way of preserving the past. The legal system would need to account for the impossibility of real-time visual documentation. Security cameras would be almost useless, showing events from minutes or hours ago rather than the present. Crimes would be investigated through physical evidence and witness testimony rather than video footage. Perhaps law enforcement would develop different methods entirely, focusing on prevention rather than documentation, since documenting crimes in progress would be nearly impossible. Education would rely heavily on direct in-person instruction. Distance learning would be impossible with slow electromagnetic communication. Students would need to be physically present with their teachers, unable to access online resources or remote lectures. Perhaps education would be more apprenticeship-based, with students learning by doing rather than by watching or reading. Or perhaps travelling teachers would move between communities, carrying knowledge from place to place like medieval scholars. Libraries would be treasure troves of human knowledge, but accessing information from distant libraries would be challenging. You couldn't simply download a book from another city. The data would take days or weeks to arrive. Perhaps libraries would maintain massive physical collections, with books being copied and physically distributed rather than transmitted electronically. The printing press would remain one of humanity's most important inventions, never superseded by digital distribution. Art and literature would reflect the temporal isolation of this universe. Stories might focus on patience, on waiting, on messages that take lifetimes to arrive. Poetry might celebrate the present moment, the only thing that can be directly experienced. Visual art would be created knowing that distant viewers won't see it for hours or days after it's unveiled. Perhaps artists would create works designed to be experienced differently from different distances, playing with the temporal delays. Music would likely be the dominant art form for live performance. Sound, travelling much faster than light in this universe, would allow for relatively immediate artistic expression. Concerts could still exist, with audiences hearing the music essentially as it's performed. But the visual element would be delayed and distorted, with distant audience members seeing the musician's movements seconds or minutes after hearing the notes. Perhaps concerts would be purely acoustic experiences, with audiences closing their eyes to avoid the visual disconnect. The recording industry would face unique challenges. While sound could be recorded and played back normally, any visual component would be problematic. Music videos would be impossible in any conventional sense. Album covers would need to be printed rather than transmitted electronically. Perhaps music would be distributed on physical media exclusively, with no possibility of digital downloads or streaming. News and journalism would operate on different timescales. Breaking news would be impossible to broadcast immediately to distant audiences. By the time a news signal reached viewers across a city, the event would be hours old. Perhaps news would be distributed more like history, with journalists focusing on analysis and context rather than immediate reporting. Newspapers would remain dominant, with physical distribution being faster than electromagnetic transmission. The concept of fame would be localized. Without global mass media, celebrities would be known only in their immediate regions. A famous actor in New York might be unknown in Los Angeles. Perhaps fame would be more like it was in ancient times, with renowned individuals known by reputation rather than image, their stories spreading slowly through physical travel and written accounts. Sports broadcasting would be nearly impossible. A game happening in a stadium couldn't be broadcast to distant viewers in anything approaching real time. Perhaps sports would remain purely local entertainment, with people attending games in person rather than watching on television. Or perhaps new forms of sports would develop that don't require real-time viewing, maybe strategic games that unfold over days or weeks. The military implications of slow communication would be profound. Coordinating forces across distances would be nearly impossible using electromagnetic signals. Armies would need to rely on physical messengers, as they did for most of human history. Radar would be useless, with radio waves taking hours to bounce off distant objects and return. Perhaps warfare would remain more medieval in nature, with local conflicts rather than coordinated global operations. Diplomacy between nations would require extreme patience. Ambassadors would truly be plenipotentiaries, authorized to make decisions on behalf of their governments without being able to consult home. International negotiations would happen through physical meetings or written correspondence, with electromagnetic communication being too slow for practical diplomacy. Perhaps the world would be more fragmented, with less global coordination simply because communication is so difficult. The concept of privacy we discussed earlier would extend to communication. Every electromagnetic signal sent would be visible, or audible, or detectable for an extended period as it slowly propagates outward. A private phone conversation would send signals crawling through space that could be intercepted anywhere along their path. Perhaps encryption would be even more important than in our world, or perhaps people would simply accept that electromagnetic communication is inherently public. Emergency services would need to be completely restructured. Calling 911 wouldn't bring immediate help if the signal takes minutes or hours to reach the emergency centre. Perhaps emergency services would be more distributed, with help available within walking distance of every location. Or perhaps people would rely more on their immediate community for emergency assistance, knowing that distant help cannot arrive in time. Banking and financial services would operate without electronic transfers. Money couldn't be wired instantly across distances. Perhaps banking would return to physical currency and written checks, with actual transport of money between institutions. Or perhaps local economies would be more isolated, with less need for long-distance financial transactions. The stock market, if it existed, would be a slow-motion affair. Price information from one exchange would take hours to reach another. There could be no global market, only local ones with prices that might vary significantly between locations. Perhaps economics would be less volatile, with slower information flow preventing rapid bubbles and crashes. Navigation. Technology would be completely different. GPS relies on signals from satellites, but those signals would take years to reach Earth in a slow-light universe. Perhaps navigation would rely on inertial guidance systems, magnetic compasses, or careful dead reckoning. Maps would be physical objects, irreplaceable treasures that couldn't be quickly transmitted or downloaded. As we contemplate communication in this slow-light universe, we see how profoundly the speed of light shapes human interaction and civilization. Our ability to instantly communicate across vast distances has shaped our global society, our economy, our culture. Take that away, and humanity would be fragmented into local communities, each developing independently, sharing information only through the slow process of physical travel. Yet perhaps there would be beauty in this isolation. Communities would be more self-reliant, more distinctive. Local cultures would flourish without being homogenized by global media. Relationships would be primarily with people physically near you, potentially deeper and more meaningful without the distraction of distant connections. The art of letter writing might reach new heights, with people crafting careful messages knowing they won't receive a response for days or weeks. We gently turn inward now, asking what it would feel like to grow up in a universe where nothing in nature is instantaneous, and everything you see is slightly beautifully old, discovering together how human consciousness, philosophy, and our very sense of self would be shaped by living in a cosmos where the present is always just out of reach. Perhaps we would become more patient, more reflective, more accepting of delay, understanding that every perception is a conversation with the past, and in this understanding we find profound lessons about time, existence, and what it means to be human. Imagine being born into this slow-light world, opening your eyes for the first time as an infant, and beginning to learn about reality through senses that deliver information at different speeds. Your mother's voice reaches you almost immediately when she speaks, but her face, mere inches from yours, appears as it was a fraction of a second ago. This tiny delay, imperceptible to us but fundamental in this universe, would shape how your brain develops its understanding of cause and effect, of self and other, of now and then. The development of self-awareness would follow a different path in this universe. In our world, babies discover themselves in mirrors around 18 months old, suddenly recognizing that the image they see is themselves. But in a slow-light universe, a mirror wouldn't show you yourself as you are now, but as you were moments ago. The delay would depend on the distance to the mirror and back, perhaps a second or two for a typical bathroom mirror. Children would grow up understanding that mirrors show the past, that the face looking back at them is not their current face but a temporal echo. This might lead to a different conception of self entirely. If you can never see yourself as you are right now, only as you were, would you develop the same sense of unified identity that we have? Perhaps people would think of themselves as existing across time rather than in a single moment, as a stream of temporal states rather than a fixed entity. The question, "Who am I?" would be complicated by the question, "When am I?" The psychology of perception would be fundamentally altered. In our world, we experience the illusion of a unified present moment. Everything we see seems to be happening now. Our brains automatically compensate for the tiny delays in light travel and neural processing to create this seamless experience. But in a slow-light universe, these delays would be too large to ignore. The brain couldn't create the illusion of simultaneity. people would grow up consciously aware that they're seeing different objects from different times, that their visual field is a temporal collage rather than a snapshot. Perhaps humans in this universe would develop what we might call temporal intelligence, an intuitive ability to calculate when things actually happened based on when they're seen. Just as we automatically judge distances based on visual cues, they might automatically judge temporal offsets. A child learning to catch a ball would need to account not just for the ball's trajectory, but for the delay between where the ball appears to be and where it actually is. This might lead to enhanced predictive abilities, with people becoming natural physicists constantly calculating trajectories and timeframes. The philosophy of mind would grapple with different questions in this universe. The hard problem of consciousness, how subjective experience arises from physical processes, would be complicated by the temporal fragmentation of perception. If you're seeing different parts of the world from different times, when exactly is your conscious experience? Are you experiencing the present even though you can't perceive it? Or are you experiencing the past that you can perceive? Perhaps consciousness would be understood not as a point, but as a temporal smear, existing across multiple moments simultaneously. Free will would take on new dimensions. In our world, we feel we have free will partly because we seem to be able to respond immediately to what we perceive. But if perception is always delayed, and if you know it's delayed, every action becomes more deliberate, more calculated. You can't react instinctively to what you see because what you see is old information. Every decision would require predicting the current state based on past observation. Perhaps this would lead to a more deterministic worldview, with people seeing themselves as calculating machines rather than free agents. The nature of memory would be different when the distinction between perception and memory is blurred. In our world, there's a clear difference between seeing something happening now and remembering something that happened before. But in a slow light universe, all visual perception is already memory. You're always seeing what happened, not what's happening. Perhaps the brain would organize memory differently, with less distinction between recent perception and recalled experience. Language and thought might be structured differently. In our world, many of our metaphors and concepts are based on visual perception happening in real time. We see what someone means. We look at problems. We have insights and outlooks. But if visual perception is always delayed, would these metaphors develop? Perhaps language would be more focused on prediction and inference. Instead of, I see what you mean, people might say, I calculate what you mean, or I project what you mean. The concept of beauty might evolve differently. In our world, beauty is often about immediate visual impact, the sunset that takes your breath away, the face that launches 1,000 ships. But if visual experiences unfold slowly, with light crawling across scenes, beauty might be more about patience and anticipation. Watching a sunset would be an hours-long experience as light from different parts of the sky slowly arrives. Perhaps beauty would be found in the gradual revelation rather than the immediate impression. Art and aesthetics would reflect this different relationship with perception. Painters might create works designed to be viewed from specific distances, knowing that viewers will see different parts of the painting from different moments in the past. A large mural might be painted so that its various sections, seen from different temporal delays, combine to tell a story across time. Sculpture might play with the fact that walking around a statue means seeing it from progressively different moments in the past. The concept of love and attraction would develop in a world where you can never quite see your beloved as they are right now. When you look into someone's eyes, you're seeing their eyes as they were moments ago. When they smile at you, you see that smile after it's already faded. Perhaps love would be less about visual attraction and more about other senses, the immediate presence of someone's voice, their scent, the warmth of their touch. Or perhaps love would explicitly embrace this temporal delay, finding beauty in always seeing the beloved as they were, preserved in the slowly arriving light. Parenting would require different skills and instincts. Parents couldn't rely on immediately seeing what their children are doing. By the time you see your toddler reaching for something dangerous, they've already grabbed it. Perhaps parents would develop heightened auditory awareness, listening for trouble rather than watching for it. Or perhaps child rearing would be more communal, with multiple adults watching from different distances to provide different temporal perspectives on the children's activities. Education would need to account for the temporal complexity of perception from the earliest ages. Children would learn that seeing is not believing, that observation requires calculation, that the present is a construct built from observations of the past. Mathematics would be taught alongside basic perception, with children learning to calculate time delays as naturally as they learn to count. Physics would be intuitive rather than abstract, with everyone growing up as natural physicists. The development of empathy might follow different pathways. In our world, mirror neurons fire when we see others experiencing emotions, helping us understand and share their feelings. But if we see others' expressions after they've already changed, would this same mechanism develop? Perhaps empathy would be more cognitive than emotional, based on understanding and prediction rather than immediate mirroring. Or perhaps it would be stronger, with people learning to anticipate others' emotional states rather than just responding to them. Social interactions would require different skills. Reading body language would be complicated by the fact that you're seeing past positions, not current ones. Perhaps people would learn to extrapolate from what they see, building mental models of others' likely current states. Or perhaps non-visual cues would become more important. Tone of voice, breathing patterns, even smell might convey more social information than visual appearance. The concept of personal space would be different. In our world, personal space is partly about visual privacy, being far enough away that others can't see your expressions clearly. But in a slow light universe, distance also means temporal delay. Someone standing close to you sees your recent past, while someone far away sees your more distant past. Perhaps personal space would be about temporal privacy, staying close enough to others that they can't see too far into your past. Trust would take on new meanings in a world where you can never verify someone's current state. When someone tells you they're smiling, you have to wait seconds to see that smile. When they say they're reaching out to shake your hand, their hand arrives before the image of it reaching. Perhaps trust would be more fundamental to social interaction, with people necessarily accepting others' words about their current states and intentions. The development of theory of mind, understanding that others have different perspectives and knowledge, would be more complex. Children would need to understand not just that others see things from different spatial positions, but from different temporal positions. What you see and what I see are not just different views, but views from different times. This might lead to more sophisticated perspective-taking abilities, with people naturally understanding the relativity of observation. Mental health and psychological well-being would face unique challenges. Anxiety about the future might be compounded by inability to see the present. Depression might be deepened by the sense that everything perceived is already past, already gone. Perhaps new forms of therapy would develop, focusing on acceptance of temporal delay, on finding peace with always living slightly in the past. The concept of mindfulness and living in the present would be philosophically complex. How can you be present when you can't perceive the present? Perhaps mindfulness would focus on awareness of the delay itself, on being conscious of living across time rather than in a single moment. Meditation might involve calculating backward from perception to imagine the actual present, or forward from the past to predict the future. Religion and spirituality would grapple with the nature of divine perception. If even light is slow, how does God see everything? Perhaps theology would develop different concepts of omniscience, with God existing outside of time entirely, or experiencing all moments simultaneously. The idea of prayer would be complicated. Are you praying to God as God is now, or as God was when the light from your position reaches the divine? The concept of death and mortality might be different. In our world, death is often understood as a singular moment. The heart stops, consciousness ends. But in a slow light universe, where perception and existence are already temporally smeared, death might be understood more as a process, a gradual fading across time. The light from someone's last moments would continue travelling outward, carrying their image long after they're gone. Perhaps this would provide comfort, knowing that in a sense, everyone who has died is still visible somewhere, their light still travelling through space. Ethics and morality would need to account for the temporal nature of perception and action. If you see someone in distress, by the time you see it, the moment has already passed. Do you have a moral obligation to respond to suffering you can't prevent because it already happened? Perhaps ethics would focus more on prediction and prevention, on anticipating problems before they become visible. The justice system would grapple with questions of responsibility and temporal knowledge. If someone claims they acted based on what they saw, but what they saw was already past, are they responsible for not predicting the present correctly? Perhaps legal systems would develop complex frameworks for assigning responsibility in a world where no one can see current reality. The concept of progress would be different in a society where communication across distances is so slow. New ideas would spread physically rather than electronically, carried by travelers and books rather than broadcasts. Perhaps progress would be slower but more thoughtful, with innovations having time to be fully considered before spreading. Or perhaps different regions would progress in different directions, developing diverse solutions to human challenges. Cultural evolution would happen in isolated pockets, with each community developing its own customs, languages, and beliefs, with minimal influence from distant cultures. Perhaps humanity would be more diverse, with thousands of different ways of life flourishing independently. Or perhaps certain ideas would prove so useful that they would slowly spread across the world, taking centuries or millennia to become universal. The concept of human rights might develop differently. In our world, the idea of universal human rights partly depends on global communication and awareness of conditions everywhere. But in a slow-light universe where you can't know what's happening on the other side of the world, would universal concepts develop? Perhaps rights would be more local, with each community developing its own standards. Or perhaps the physical movement of people would carry ideas about rights and dignity from place to place. The meaning of life itself might be understood differently. In our world, many people find meaning in their impact on others, in being seen and remembered. But in a slow-light universe where being seen is always delayed, where your image continues travelling long after you're gone, the relationship between existence and perception would be more complex. Perhaps meaning would be found less in being perceived and more in the actions themselves, in the changes you make to the world regardless of whether anyone sees them. As we reflect on human nature in this slow-light universe, we see how profoundly the speed of light shapes not just our physical experience, but our psychological, social, and spiritual development. We are creatures of light in a very real sense, our consciousness shaped by the speed at which information reaches us. Slow that light to a crawl, and human nature itself might be fundamentally different. Yet perhaps these humans would be more thoughtful, more patient, more accepting of uncertainty. Living in a world where the present can never be seen might make them more comfortable with ambiguity, more skilled at prediction, more aware of the temporal nature of existence. They might develop forms of wisdom that we, with our relatively fast light, cannot achieve,